Okay, so colleagues and office friends, so let's start with today's workshop. So okay, welcome to today's workshop. I Dr. William from Wilson. So this is our third time to organize this workshop in the ITC conference. It's working about the safe and certifiable navigation and control for the IVs in complex urban areas. So I just quickly go through because our first presenter, Professor Tim Barfoot, is going to leave at 9 o'clock. Okay, so I just quickly go through maybe 1 to 2 minutes. So today we organizer includes okay me and Daniel Mandela, Dr. Daniel Mandela, and Dr. John from Beihang, and also Xi Wei and also Hao Ming. Okay, great offers from Hao Ming. So also we have organized from Nanyang Technological University. So I just quickly go through our. Okay, so the challenge, okay, transfer into the opportunities. Okay, we are getting older and older. We have robotics and like drones and cars, ground vehicles and air vehicles. So currently, I always like to use this figure to illustrate the long tail phenomenon. So I mean, the green area is the happy area. Okay, we like solve the problems from like in the past years for the unmanned air vehicles and ground vehicles in majority of the scenarios. But the challenge is that I mean, especially like the auto-driving industry is quite okay, silent recently, especially because we are diving into a long tail area. It means like 98 of the challenge have been resolved already in the majority of the scenarios. But currently we have like maybe 2% of the challenges may take around like 90% of additional time to resolve this challenge. So let's elicit the incentive or the initiative of this workshop. So we have organized this workshop for 3 years. So I mean, for example, I wish to take this figure in Hong Kong to say, okay, let's say the long tail scenarios with like challenges for your positioning, maybe for your control and how to certify your system is certifiably correct. So okay, so this is the name of this workshop. This is highly expected. So let's quickly introduce today's talk. So okay, it's a great pleasure. We invited several okay prestigious speakers, including Professor Tim Buffer. He's going to present the first talk. So and also Professor Kong Hui from University of Macau. So he's a very good expert in the field of robotics. So previously he also have experiences in the robotics, and also I mean during the transition of each speaker, okay, we are going to have the introduction by Xi Wei and by Hao Ming later, okay, for more details. And also Professor Xu from PolyU, so previously experts in the field of navigations and the safety for the navigation. So also Dr. David Rosen, so I mean very famous researchers in the field of robotics. Okay, so that's why I try to make this workshop to be interdisciplinary, including the research from GPS, from aerospace, and robotics, like the Rosen from like Robotics Society, and also Dr. Medilami from IT Society, ION. So to make this to be interdisciplinary, and also Dr. Matt from okay Robotics Society, and also Dr. Yang from maybe like auto-driving industry, like mapping localization stuffs. So that's roughly about the schedules for today's. I mean the schedule for this morning. Okay, for each talk, it's going to be roughly around like 30 minutes with several minutes for the QA. So this is roughly all for today's talk. So, okay, so I think I can pass the time to Professor Tim Bufford. So Professor Tim Bufford, can you hear me? So Tom, you organize the first.
Yep, I can hear you. So thank you very much for the invitation to give a talk at your workshop. Sadly, I can't make it to ITSC this year. The last time I went to the conference, it was in Hawaii. So I hope you enjoy it as much as I did when I was in Hawaii. Although I guess you're in Edmonton, so we'll see how that goes. The title of the talk, Taking a Hardline, Robot Navigation When Lighting, Weather, and Geometry Won't Cooperate. So this is my agenda, a bit of a graphical agenda for the talk. It's broken into 4 parts. I'll talk a little bit about how we've been using some Doppler sensors, both LiDAR and radar, to help us navigate on the road. I'll jump then into localization on the road and where we've been trying to make some improvements there. I know you're mostly focused on urban driving in this workshop, but I work also on off-road driving, so I just wanted to talk a little bit about some of the things we're doing there. And then if time permits, I'll talk about some of our contributions where we've been working on global optimality certificates. Although I think Dave Rosen and Matt Giamou are going to talk a lot more about that, so I may just basically serve as an introduction to what they're about to talk to. Okay, let's jump into the first topic. So Doppler odometry. We've been working quite a bit with these two sensors for the last couple of years. On the left, we've got a Navtec imaging radar. So it's the 360-degree spinning radar. You can see the data product that's coming off that sensor in the little video. And on the right, we've got a probably less well-known sensor called a Doppler LiDAR. This is from a company called EVA. And the point cloud that you're seeing in the video is basically colored by the relative velocity between the ego vehicle and the scene. And so you can see the other vehicles show up as brightly colored things because their relative velocities are quite different from the background scene. And of course, we can do some very interesting things with that. So I'll talk about some of the things we've been doing with these two sensors, particularly ego motion estimation on the road. First of all, let's just talk a little bit about what is a Doppler sensor. So I think most of us are used to sensors that produce point clouds, and they do that using a time-of-flight ranging principle. These Doppler sensors use a slightly different ranging principle called frequency modulated continuous wave. And the idea there is that you're sending out a modulated wave. And in frequency space, that looks like a ramp. So it's getting faster and faster in its frequency as you send out this signal. And when the signal bounces off something and it comes back to the receiver, it basically results in this green offset in the time domain frequency profile. And by looking at the gap between these things, we can get an estimate of the amount of time spent in the flight of the signal. And it turns out that if you use these are called up chirps. If you also use some down chirps where the frequency is getting slower over time and alternate between up and down chirps, you can not only get the range, but you can also get the relative velocity between the sensor and the scene in front of it. And so that's quite exciting because it means you're getting native velocity information directly off the sensor rather than having to sort of maybe compare two point clouds to try to indirectly derive velocity information. And what are the advantages of using a sensor that can measure this new type of thing? Well, there's the obvious thing, right? If we look at these point clouds, the colors of these other things, which are colored by velocity, it would be fairly easy for us to segment out moving objects on the road, for example, just based on their velocity information. So if they're moving quite differently from the background scene, segmentation basically almost comes for free. So that's kind of an obvious thing. A less obvious thing is that if we can get relative velocity information to the scene, we can actually start to estimate our motion even in challenging scenarios that normally wouldn't be possible with just the point cloud information. So we can even estimate our motion. The most pathological example is a long straight tunnel. So if you're trying to match two point clouds along a tunnel, there's an infinite number of places where you could make those point clouds match. But with the velocity information, we can still get good motion estimation through a tunnel, as we'll see. And then an interesting side benefit that we notice is that this is actually point clouds from, in this case, what you're seeing right now is the EVA LiDAR. And then this is a Velodyne LiDAR. And you can actually see this is actually in the middle of a snowstorm. So all this clutter is from snowflakes. But because the EVA LiDAR is using this up chirp, down chirp, you can actually on hardware filter out things like precipitation from the scan. So that's kind of an interesting side benefit that we notice with using these sensors. Here's just another view of the EVA LiDAR in this case. So I'm going to talk a little bit about estimating motion from LiDAR for the next few slides. So this is the point cloud that we're getting. And this is just a camera view just for context. And you can see this is our Doppler-aided LiDAR odometry. And you can see we're tracking ground truth very nicely along here. Actually right on top of the ground truth over multiple kilometers. And a lot of that is enabled by the fact that we've got extra velocity information that we can make use of. So let's see a little bit about how that works. Oh, actually, I think I'm not going to show exactly how that works, but here's an example of a pathological situation where regular LiDAR odometry does not do too well, but the Doppler version does pretty well. So this is a long tunnel. It's actually called the Robin-Williams tunnel. And it's very challenging to match point clouds along this. You can kind of see there's a ground truth estimate, and our Doppler-aided estimate is tracking that quite well. but then a regular point cloud sort of ICP method falls quite short, and it's because it has trouble trying to estimate the motion along this long straight environment. So we're able to do pretty well in there. More recently, though, we've started thinking about, well, if we have this velocity information, do we even need to do something like iterative closest point at all? So many of us are probably familiar with estimating motion by getting one point cloud, moving, getting another, and then matching between those using something like the iterative closest point algorithm. We wanted to sort of turn that on its head. The most expensive step in iterative closest point is finding the correspondences between one point cloud and the other point cloud so that you can do the matching. And now that we have the velocity information, we kind of asked ourselves, could we actually just skip point cloud matching altogether and just estimate the overall platform velocity in 6 degrees of freedom, and then just integrate that over time to get the overall motion of the platform after the fact? And it turns out we can do that reasonably well just with one of these Doppler LiDAR sensors. It turns out that there are some observability questions that you need to ask. If you have just one Doppler LiDAR sensor, you can actually only get the velocity information in the radial direction of each beam. And so from one Doppler scan, you can't actually estimate the rotational motion of the platform. We did an observability study where we looked at using 2 or 3 of these Doppler sensors that were not co-located on a vehicle. And theoretically, with 3 sensors, you could actually measure the full 6-degree freedom velocity of a platform. We tried actually to do that in practice, and it turns out that there were some challenges to make that work really well. So the results I'm going to talk about today are just using one Doppler LiDAR, but also a 3-degree freedom gyro to measure the 3 degrees of rotational motion that the Doppler sensor can't measure directly. So we took one of these Doppler LiDARs and we took a simple 3-degree freedom gyro, and we put them on a vehicle, and we built up an estimator that's using a basic factor graph kind of format. In this case, the state that we're estimating is only the 6-degree freedom velocity, and then we have factors for the translational velocities coming from the Doppler LiDAR point cloud and factors for the heading gyro for the rotational degrees of freedom. And we put that all together into an estimator. And it turns out it's actually a linear estimator. So we can run this, basically you could run this just using the Kalman filter, not the extended Kalman filter, to estimate the overall 6-degree freedom velocity of the platform. Then of course you have to integrate to get the pose, and that's not going to be linear anymore, but the estimator itself can be posed as a simple linear estimator. And that's because the measurement models are both linear. Here are some results of what that looks like. We're not doing as well as the state-of-the-art ICP-based LiDAR odometry. So black is ground truth, orange is sort of a state-of-the-art algorithm, and green is our estimate that we got from this really lightweight Doppler LiDAR odometry that doesn't even do correspondences. So we're a little less accurate, but we really win on the processing time. So we can process each LiDAR point cloud in about just under 6 milliseconds. So if you wanted to run this on an embedded compute, it actually does pretty well. And then in these geometrically degenerate situations, we do really, really well compared to just a point cloud-based method, which I showed you before. So I'm going to switch a little bit now to using radar. So I showed you how to do Doppler odometry using LiDAR. Now let's talk about how could we do the same thing with one of these imaging radars. And it turns out we were able to get a firmware update on the Navtech spinning radar that allowed us to get velocity information off it. Out of the box, it doesn't do that, but we work with Navtech closely, so we're able to get an update that provides some, actually, they don't actually directly provide the velocity, they provide some information that's related to the velocity. So unlike the LiDAR, it doesn't directly provide velocity. So we had to do a lot of low-level signal processing to try to match the full waveform coming off 2 consecutive azimuths in this radar. And from that, we were able to derive a velocity estimator. So all of it's actually much, much noisier than the Doppler information coming off the LiDAR because it's longer wavelength. But we were able to reject a lot of the really bad measurements using RANSAC and produce an overall translational velocity for the platform from one radar scan. And then again, we can then turn that into an estimator and integrate that over time to get the overall platform motion. We did some testing of this in a number of different environments. So suburbs, highway, tunnel, and a skyway, a big bridge. And from left to right, these are progressively more difficult environments in the sense that they have less and less usable information in each scene. You can see even just the radar scans look a lot simpler as you move from left to right, which makes it more difficult to estimate motion. But because we have this added velocity data that's coming off the sensor, even in something like this tunnel or on the skyway where we don't have a lot of information around the vehicle, we're able to estimate motion pretty well. And here are some of the results of the way that looks. So in suburbs and highway, I guess our new method is the green one. And maybe a more classic iterative closest point algorithm is the blue line. So in very cluttered urban scenes, we do about the same as these more classic algorithms. But as soon as you get into the geometrically degenerate situations like tunnels and bridges, you can see that the classic algorithms are failing to estimate motion properly because of the degeneracy of the environment. So that's where the geometry is not cooperating, hence the title. And you can see that we're still able to estimate motion pretty close to the ground truth, which is shown in red. So this was, and it's much lighter weight, actually, I should mention. So this was quite promising for us. So that's a little bit about Doppler odometry. I wanted to switch to localizing on the road and give you an update on what we're doing there. So if you haven't checked it out, I recommend checking out our dataset, the Boreas dataset, which is a publicly available dataset. It's got over a year's worth of data with all 4 seasons in Canada. So you're currently in Edmonton, but you're not there in the winter, and it's going to look pretty cold in the winter if you were to stay there. So there's lots of usable data there. There's radar, LiDAR, cameras, and post-processed ground truth. It's all hosted on AWS, and there's a leaderboard. So if you're interested in this type of localization and mapping work, you can check that out. We've built in the past, and I've reported in the past on a couple of different localization pipelines. So now we're not just doing odometry, we're actually building a map, and then so we do odometry first to do mapping, and then we localize against that map. So now we're referencing a map in order to determine our pose on the road. And I won't get into the details of that. So the map matching is based on iterative closest point. At the moment, we're sort of state-of-the-art, close to state-of-the-art on our LiDAR pipeline, so we can determine where we are to within about 5 centimeters on the road. And our radar pipeline, which also uses iterative closest point, we can determine where we are to about 10 centimeters on the road. So we're not quite catching up to LiDAR, but we're getting close. Here are some more detailed statistics about how our different localization pipelines are doing on the road. So I may have been actually even pessimistic. Our LiDAR data is down to about 4 centimeters of longitudinal and lateral error. Our radar to radar matching, so build the map with radar and localize with radar, is sort of down to about 8 centimeters. And the other thing we tried is building a map with LiDAR and then matching radar scans to the LiDAR map. And we're not quite catching up with the other two. We're actually a little bit worse on that, as much as 12, 13 centimeters of error. But there's quite a big difference in the modalities there that we still need to work on in order to improve that a little bit further. But that might be of interest if you wanted to use some existing LiDAR maps, but then still localize in bad weather. I guess I didn't say at the beginning that our interest in radar is really to do with bad weather because of the longer wavelength it can see through thick precipitation, fog, snow, rain. It's pretty unaffected by those things, whereas the other sensing modalities that we're used to, LiDARs and cameras, are more affected by that. The other thing we've been thinking about is not just building better localization algorithms, but really trying to, and this goes to the title of this workshop, trying to understand like where do these algorithms break? And one of the things we've been thinking about is the idea of adversarial attacks on our algorithms. So imagine you're using iterative closest point to match a scan to a map. You would really like to know, is that map actually going to be a safe map for the robot to localize against before you deploy it into the real world? And I guess what we've been trying to do there is build some kind of tools that will try to trick the algorithm into producing bad localization. So could we take the point cloud that's coming off our sensor, do some processing to it to produce some corrupted version of that point cloud that is able to trick the algorithm into thinking the data is good, but then to produce a large localization error. And so one way we've been doing that is a generative AI kind of approach where we've been trying to maximize our localization error by corrupting point clouds using this network approach. And if you were to do that and then process one of your maps before you deploy on it, you could actually build a heat map that sort of shows, even before you start driving, what is the worst place for localization? What is the best place for localization? Where are we likely to get the worst errors and the best errors? And I'll just stress that it's very easy to make a really bad corruption to a point cloud. The trick is to finesse it so that you get just enough corruption that the algorithm still accepts the data. Because if we have something like truncated or trimmed, I should say, ICP, we can easily throw away some of the data if it's really bad. So really we want to trick the algorithm into accepting the data but still produce large errors. And then you can do things like analysis of maps to figure out where you're likely to have localization problems. So we're going to keep going in that direction because I think that's a really nice use of AI, where you're not actually even putting it into the safety loop, but you're getting some useful work out of it. A little bit about off-road. We've been working a lot on this visual route following framework called Visual Teach and Repeat for a lot of years. The idea here is you drive through an environment once, you build a set of maps along that path that you've driven, and then you have the robot automatically localize against those maps and then close a loop so that it's able to drive exactly in its tracks. So that's actually how our localization pipelines work on road as well. We drive the environment first, and then we build the maps and then localize against them. The difference here is that we're also closing the loop around the signal that we're getting back from the localization in order to drive exactly in our tracks. So we've done a lot of this work with vision in the past over many years. We also do this with LiDAR. So you're seeing here our most recent LiDAR pipeline. This is actually about a year ago now. In this case, the robot is driving in its tracks in a very, I guess, challenging geometric environment. These sort of undulating hills are not very conducive to getting good geometry for localization, but we're getting enough off things like that building to know where we are. But we're also detecting and avoiding obstacles that have been placed on the path between the teach and the repeat. So the robot's able to make a small detour around those and then get back in its tracks and then follow along the path still. So I guess you could do a similar thing on the road. We mostly do this testing off-road because it's a little bit easier than putting an autonomous vehicle on public road. One of the things that we've gotten excited about lately is an old idea. So going back to the idea of intensity imagery. So we spent a long time looking at this almost 15 years ago. We had a very custom LiDAR that was able to produce these high-quality image-like data products from a LiDAR. And we were able to run vision processing from 15 years ago on these to do interesting things like estimate motion. The game has changed a little bit since that time. And for a long time, there weren't any commodity level LiDARs that could produce good quality intensity images. It turns out these Ouster 128 beam LiDARs are producing pretty nice quality intensity and range images now, to the point that you can run computer vision models on them. And one of the things we've been looking at is, of course, deep learning has come along since we had these old LiDARs. One of the things we've been looking at is for detecting obstacles and objects is to run things like the Meta's segment anything model directly on these LiDAR intensity images. And the nice thing about that is you get a small domain gap because LiDARs pretty much look the same under any lighting condition. And so the thought process is, can we get the benefit of having been trained on a lot of data, but then still sort of know that the domain that we're going to be running the model on at test time is actually fairly well understood. It's not going to suddenly have a totally different looking image because of lighting. And one of the things we can do then is we can extract out different masks. And if we wanted to know if something has changed in the environment, here's an example where a barrel was placed in the scene. The segment anything model extracts a mask on this barrel, and we can compare it to the masks that we had when we taught the path. And if those look totally different, then we say that there's a change. And we can then label that part of the scene as different. And of course, we haven't had to assume anything about the classes of the objects in order to do this. We're just using basic segmentation of the scene on a LiDAR image to do that. And we can then use that to avoid obstacles that have been introduced to the scene. The most recent thing, this is very hot off the presses. This video just got created yesterday. This was submitted to ICRA. We're also now doing radar teach and repeat. So this is a brand new result from our lab. We weren't too sure this was going to work in off-road environments because you can see very there's not a lot of useful geometry happening in this bushy off-road environment, which is why we're testing there. But there's enough repeatable geometry between the teach and the repeat that we're still able to localize and drive within, 10 centimeters error in this challenging off-road environment. So we're pretty excited that that worked, and a little surprised, to be honest, that it worked as well as it did. And here you can see just a comparison of different radar scans. This is like lots of useful man-made structures in here. This is the off-road environment you just saw in the video. And then this is actually even a forest trail where it's very three-dimensional and the radar is pitching up and down. And you can kind of see that there's ground strikes in the data. So there's still work to be done. We can't do radar teach and repeat in all off-road environments yet, but we think that we're close enough that it's probably going to work with some more features added to handle these even more challenging environments over here. And actually, to that end, kind of like the Boreas dataset, we've been building a new off-road all-season dataset for off-road driving called the FOMO dataset in collaboration with the University of Laval. That's work in progress, so stay tuned. Hopefully, you'll see that within a year. Looking at the clock, I probably don't have time to talk about this last topic, so I may just defer to Dave and Matt to talk about this later today. But I'll give you the intro, which will maybe help them. So many of these algorithms that I've talked about, localization, mapping, and also planning and control, are often set up as optimization problems, factor graphs, and the like. And if you open, any book on state estimation, typically we're pretty much happy to just find local minima of the cost functions that we set up. But it turns out that means you need a pretty good initial guess in order to get your algorithms to converge to the correct local minimum. And that can be challenging. And so one of the things that we can do to improve safety of robots is to actually invest time in developing solvers that don't require these good initial guesses. And there's been all kinds of great work, including stuff from Dave and Matt, who will get into this in a lot more detail later in the workshop today. But there's all kinds of great work that's been happening to improve some of these algorithms that we make use of frequently in robotics so that we can solve these optimization problems globally instead of locally, which is it removes one of the places where there's a concern that we just might have an algorithm failure, which I kind of think of as an unforced error, right? We don't really want that to happen. So they'll get into that in a bit more detail. My group's been working on some related problems, which I guess I won't talk about, but lots of fun stuff happening there. So I'm actually probably going to wrap it up there. I got to do all the talking, but there's been many people and companies supporting the work over the years. So I'd like to thank all of them. And then I'll just maybe stop there and see if there are any questions about what I talked about. Thanks.
Daniel here. Thank you very much for your super excellent presentation. I was curious about the mapping comparison between the LiDAR and the radar. I'm curious about what are the, let's say, memory consumptions in terms of mapping when compare LiDAR and radar.
Yeah, that's a great question. So the mapping and localization that we do with LiDAR is in pretty much 3D. The radar that we're using is scanning only in 2D. So we build 2D maps and do 2D localization. So the radar is much cheaper to do, but obviously there's going to be some limitations as to what you can do with that, right? We're already seeing in the forest environment that as soon as the radar is going up and down, we're seeing it striking the ground, which is sort of violating the 2D assumption that you're making when you're building maps with that sensor. There's also been some really cool work recently where people are trying to build 3D maps from like 3D volumetric maps, kind of like NERFs, using 2D scanning radars. We haven't really looked in that direction. But generally, yeah, radar is much cheaper to store, but it's going to come with limitations, I think, in terms of what environment you can test in.
And you mentioned rotating radars. Do you have in your roadmap also this type of MIMO frequency modulated radars that maybe they could potentially produce a point cloud?
Sorry, I didn't quite get the question. Can I recommend a specific unit? Is that what you're asking?
Sorry again, I couldn't hear you. So I was asking about MIMO radars. So this type of, instead of rotating ones, but still they are static, but they have multiple channels being processed as in a single receiver. Do you consider they're using the feature?
Well, I'll say a couple of things about that. So the spinning radars that we're using do get used in mining, actually. So like the group at Örebro University in Sweden has been using the same Navtech radars for mining applications for quite a while. So it doesn't mean you have to switch to the phased array style static smaller field of view radars. But there are some advantages of that, right? So in automotive, we don't really see these spinning radars too often. These come more from like the marine world. But the automotive radars, like the fixed phased array, fairly narrow field of view, you put lots of them around a vehicle, you can probably do very similar things to this. Most of the localization and mapping, I would say, works well when you've got a fairly large field of view, overall field of view from your radars. So if you can get the coverage from several smaller radars, I think that's probably also fine.
Thank you very much.
No question. Anyone else? Please.
I probably have time for one more, and then I have another meeting I have to go to, unfortunately.
Last Grundhöfer, hello. Thank you again for the nice talk. I was wondering where the bias in the Doppler measurements come from, because to my understanding, there shouldn't be any bias to these measurements.
Yeah, good question. So, sorry, in which sensor, the LiDAR or the radar?
The FMCW radar.
In the radar.
You had a slide where you showed that you estimate the bias, and I was wondering where this comes from.
Yeah, there's a few things, I guess, right? So there's some questions about like the assembly of the radar itself, right? So you've got a transmitter that's actually hitting a rotating mirror inside the radar dome. So there's some bias from the calibration of that, right? Trying to understand the geometry of that correctly. So you can calibrate some of that out. There's also motion distortion effects. So it's only spinning at 4 hertz. And so we're moving relatively quickly compared to the rotating speed of the radar. So if you don't account for that spinning motion really, really well, that can introduce some problems. So there's lots of little details to be worked out to be able to move quickly with a slow spinning radar.
Okay, so when I understand your answer right, it's due to the geometrical 2D positioning and not to the actual Doppler frequency.
Yeah, I mean, there's a potential also that maybe you don't know the slope of your frequency chirps exactly, right? There could be some issues there. Every step in the pipeline has the potential to have bias. I would say that probably the signal processing is the most well understood part. That's been calibrated reasonably well. And I guess, geometry of putting the thing on the vehicle and dealing with the motion distortion effects is less understood.
Okay, thank you.
Okay, the title of my presentation is Autonomous Robot Mapping in Urban Environments. So why do we need robots exploration and mapping? So there are a couple of reasons. First, commercial, because like we need a sweeping robot, food good delivering robots. So that's why we need some kind of map for the navigation of the robot. And some other things like we need robots to replace humans to enter dangerous areas, such as underground mines, for the search and rescue tasks. And also we need robots in the deep sea and spaces. So what we need the robot to explore and map in the cities. Usually we need a robot to do the map representation. So there are kind of different kinds of map representations. You can see there are 2D OGM, 3D OGM, elevation maps, and so forth. Okay, so how to do mapping? So mostly for most existing commercial applications, human drives the mapping vehicles to do, collect road data and create different map representations offline. But there can be some issues with this way, because due to the road under construction, and some like earthquakes, this natural disasters, or the season changes, the Rosens always change. So that's why the long-term mapping by manually driven vehicles is not a good way. In addition, manually driven mapping vehicles, they cannot do a good job in some internal road scenes, especially like in Asian cities, especially in the residence societies. So these roads are quite small. That's why the mapping vehicles usually cannot do the job. So alternatively, we can let robot do it in the large-scale urban environment. So for that, the robots need to have the following capabilities, like plan the path, analyze terrain and traversability, estimate the ego pose, also can be aware of the extent of pose uncertainty. If the pose uncertainty is large enough, the robot should activate the loop closure procedure and find the optimal loop closure route. And also sometimes maybe the robot should preserve some loop closure keyframes. And finally, should create efficient and local and global map representation online. So all these capabilities should be done online and also in real time. So this is quite a challenging problem. And we also hope the robots can work day and night. So at the University of Macau, we do some trials. We use the robot dog, which is equipped with a DJI Mate 330 LiDAR with a built-in IMU. The IMU is tilted. The LiDAR is tilted up to 30 degrees for better terrain and traversability estimation. Although the robot dog has a built-in camera, but we haven't used it for this work so far. The computer is just an onboard computer. Okay, to start, so then we start the first trial with a local exploration approach. This approach is actually want to guide the robot with the optimal of frontier, so that the robot can follow the optimal frontier to the next step. So we propose a concave Hall-induced graph gain to do that. So we know that the frontiers are basically the regions at the boundary between open space and unexplored space. So the conventional approach finds the frontiers based on volumetric gains, but this volumetric gains has some problems. So we propose the graph gain. This graph gain is based on a concave Hall, based on the observation of the LiDAR frame. So at the neighbor, especially the inside of the neighbor, inside of the concave Hall, we find those frontiers which has the largest graph gain. So we can let robots to go to the frontier with the largest graph gain. So this approach can work very well in some regions like this kind of scenarios with this kind of a tunnel, artificial tunnel created by the railings. So this kind of scenarios usually is quite challenging for the current method. And also it can deal with some situations where the current frontier-based method can do the repeatedly exploration. So here we have some demos. Like these are in the simulated environment demos. So here we have some real-world demos, like in this local areas of University of Macau campus. Okay. So the local exploration method can work well in the local areas, but there are some issues. The first issue is without global guidance or global view, it can generate many meaningless paths, so which can result in inefficient exploration strategies. The second thing is local exploration usually works in a small area, but due to the accumulation in post-drift, then the long-term exploration in large scales usually can fail. So we propose an OpenStreetMap guided robot mapping in large-scale urban environment. There has some method using all OpenStreetMap-based guidance, like this one, using the OpenStreetMap for autonomous navigation, based on the GPS coordinates of the OS data and the observation of the LiDAR sensor. So this work using active loop closure strategy to correct the post-drift at a local scale, but this work does not have the global guidance of the OpenStreetMap, so that's why it can work in local areas. So this work also use the OpenStreetMap-based method, but this method only works in a simulated environment, so it doesn't consider the traversability between the nodes. So our method is also based on active local closure strategy for OSM-guided robot mapping in large-scale urban environment. So our methods start with the global path planning using the Chinese postman problem to find a best global path. And based on global path, like this global path, so the robots follow the global path, and then after some time, because the accumulated post-drift, so the robot can be aware of the uncertainties of the post. So once the post uncertainty is large enough, the robot will trigger the local replanning based on the active loop closure process. At the same time, our method can also simultaneously estimate the traversability and the terrain of the environment based on the random forest, because we consider the edge computer which is used in the robot. So after we find the traverse regions, we will correct the waypoint which is provided by OSM data, like in the GPS coordinates in the OS data has some errors. So we want to correct this waypoint. We want to correct this waypoint. So this waypoint can be corrected so that the updated waypoint is always located in a traverse area. We tested this method in 5 different scenes of our university campus. So experimentally, we found our method with the active loop closure strategy, we can decrease the instant uncertainty with travel distances very sharply. So here we have one demo. Like this one starts the active loop closure process here. Okay, here we have more demos. Okay, we also tested our method at night because we're only using the LiDAR sensor. Okay, the OSM-based robot mapping can work quite well in most regions, but there are two issues with the OSM-guided robot mapping. The first one is the error of the GPS coordinates in the OS data. The other issue is the OSM data are not complete in most urban areas. So the robot cannot fully cover the whole area with OSM data available. So that's why there are two ways to try that deserve try for complete coverage. The first one is maybe we can create a map created based on the incomplete OSM. Then we can do further exploration, the local exploration to get the complete mapping of every corner. The second things we try in a cooperative mapping by the ground robot and aircraft. Like we're using the aircraft as the cooperative robot to get the full coverage of the OSM data, which is based on the segmentation of the road regions. Then we staging these road regions to the alignment with the incomplete OSM data. And also based on the GPS interpolation, we can get a full coverage. Okay, so this is the idea of the exploration. I think I'm running out of time. I still have one more work, which is for map representation. That is the LiDAR atlas. So this idea. Okay, so this is the OSM maker. We are using binary deep neural network based on the UNet architecture. We do the binarization for each module. We can get pretty good results. The accuracy, but at very low computational complexity. Okay, here's the 3D LiDAR roadmap, which is a low memory cost map representation method. So the basic idea is to use the LiDAR to do the online mapping, and then we can get the traversable regions, also to get the vertical features, which is encoded by the binary features. And also we can embed global feature representation, like we are using LiDAR arrays for each key frames. So this one can be used for navigation and path planning. So we can get a pretty low memory cost. Okay, so here are some papers that we also open the source code along with these papers. These papers are all related to the presented work today. Okay, thank you.
Hello, Professor Kong.
Hi.
Thank you so much for your detailed and informative presentations. Now, can you hear me?
Yes, yes.
Okay. And now we have 10 minutes Q&A. where you can ask questions related to the topic. Any question?
So, Professor Kong, okay, okay, let's talk. Can you hear me?
Yes.
Okay, so I mean, it's really interesting, like combine the OpenStreet map. So, to my understanding, it's like if you talk about LiDAR, okay, I mean, the accuracy is like centimeters level. I mean, in terms of LiDAR accuracies, right? So actually, if you talk about OpenStreet map, like I mean, accuracy is like maybe like several meters. So how do you combine the information from OpenStreet map? I mean, accuracy is like meters level, and for LiDAR, it's like centimeter level. How do you combine the two information?
Okay, it's a good question. Actually, we don't use the OSM data for localization because we're only using the OSM data, like the GPS information in the OSM data for guidance. Although the GPS information has some errors, like up to a few meters, but we can correct the guidance point based on the observation of the LiDAR observation.
Oh, I see. So just one more quick supplement thing, so as you know, like OpenStreetMap is not quite. I mean, some of the components like the lane lines may not be available in the OpenStreetMap. So, do you think it's possible, like for example, you have the LiDARs with the guidance from the OpenStreetMap. So, do you think it's possible to build the map simultaneously to update the OpenStreetMap?
Yes, that's a good point. I think we can do this because we can let the robot do the mapping, so we can get a quite good map, and we can also do a kind of interpolation based on the map to correct the OSM data.
Okay, so just one more quick question. So, Kong, I know that before you have like several years industry experiences. So currently, I mean, in the auto-driving industry, we also have a question. So I see Dr. Yang previously is also working in the mapping localization industry. So recently, I mean, industry, especially in China, they thinking about like do we really need the maps like for attention industry? So may I have your views like for example, from point of view of positioning purpose, do you think the map is necessary? Like I mean, the HD map.
That's a good question. I think map for robots definitely is necessary, but for autonomous driving, especially the autonomous autonomous cars. We can apply the vision based based on the deep learning approaches to infer the BEV, like especially those BEV map, also based on the OpenStreetMap or the GPS information for guidance. But that is just for the autonomous driving scenarios, because autonomous driving scenarios, we have huge amount of data. We can train the model. Right? We can train a very good model. But for robotics, the scenarios can be tons of times of complex than the autonomous driving scenarios. So that's why I think map maybe in the near future, maybe for the next 10 years, maybe we still need the map, especially for the navigation.
Okay, so we understand. So any further questions?
Thank you to the committee for having us. Can I hear? You hear me clearly?
Yes.
I don't feel there's a mic, but okay, I'm loud, so it should be fine. Yeah. So I gotta give very different talk comparing to the previous two. So I'm coming from the aerospace sector. So we talk about satellite navigation much more. So my team also working on all the LiDAR stuff, but here I want to bring a different concept, which is protection level. So we're going to talk about satellite navigation. How can I make it work? I don't know. But can I just... Okay, so I'm going to talk about satellite navigation. Think about like the visual, so smart. Satellite navigation for integrity monitoring. Okay, so integrity. So what is integrity? After I talk about it, I'm going to talk about why we have to model the non-Gaussian noise. Super important. Yeah. Starting from the first. So what is integrity? Integrity in our field, we believe that that's a quantifiable measure of how reliable the system is. Looking at this example, so we're going to talk about like 99.99999% integrity. That means only 10 to the order minus 7 that you're going to have an event that is unmonitored and is hazardous and that will endanger human life. Okay, so that's the integrity means in aerospace. So we put it to our concept in intelligent vehicle. So the green star is our true position. The red star is estimate position. This is pretty stable, pretty accurate. So we're going to say we won't have this in 99% of 99 of the time. So what's the integrity risk? When you have the wrongly estimate positions very far away from your true position, and you believe that, oh, so you are in the intersection, you're going to turn right, right? So you're going to turn right, but actually a car's coming by. That's very dangerous. So we don't want this in 10 to the order minus 7%. That's what integrity means. But here's the question. It's like, okay, my estimate position and true position, the arrow is pretty big, right? How big? And why? How big is too big? So who is the one to say how big is too big? So look at this. In our sector, the authority defined this. Like in aviation, FAA defined this. In the road, DOT defined this. So the authority coming to define something called alert limit. So that means the amount of positioning error that your system can accept. All right. So look at this. This is a positioning arrow, the green arrow there, this positioning arrow. If I define my alert limit is 5 meters, like this. So around my estimate position, I believe my position is around that 5 meters, right? I want this. Do I want this to happen? So you see the arrow is much bigger than alert limit, right? So I want this happen only at 10 to the minus 7 of the time. Okay, that's what I mean about like this is hazardous. And we want to use a mathematical equation to quantify this. So this called probability of integrity risk. If you look at the, this is a conditional probability. Oh my God. So I have to walk to here. So I hope I'm loud enough. This is really hard. So look at this. This is probability. And this is our positioning error. This is a conditional probability that our positioning error is larger than alert limit. And I didn't alert the user. I want this probability that is smaller than 10 to the order minus 7. That's what we talk about integrity risk. Okay? So if we can have this, we can estimate this all really good. So I know my positioning error, I know alert limit, and I can tell my user if I'm good enough. It's all good, right? But there's only one question is, we don't have ground truth. How do I know my error? How do I know my error? That's the problem, right? Chicken and egg. So the system engineer, they believe the solution is like this. We have to estimate so-called a potential level. Previous one, the orange one, is defined. This one is estimate. We have to estimate this. So we need to estimate the potential level to bound the error. So like this. This is our estimate position. This is potential level we're trying to estimate that can bound our error. Bound how many percent of the error? Previously, we see this equation already. We want to bound 10 to the order minus 7. Our position error, we want to bound this. Now, we want to find a potential level that is designed to ensure that this position error larger than potential level, smaller than 10 to the order minus 7. That's what we're trying to do. So we're going to do an equation like this, trying to find the potential level that making this probability equals to 10 to the minus 6. This is how we do. This is what we're trying to do here. And how do we do it? In fact, we're trying to estimate this using statistical behavior. I will talk more about this along my talk. Oh my God, it's already 6 minutes. Right. Okay. Then look at this. So when we have to talk about the position level and alert limit, so we're going to talk about this, the relationship of the two. So when we have a system like this, this is your estimate position, but this is your authority defined alert limit. And this is the potential level you can estimate. That is fulfill the previous equation. What does this mean? Your position could be scattering around the blue dot, but you actually only want the position scattering around the orange dot. That means your system, you cannot confirm it's safe or not, right? So in this case, potential level larger than alert limit is the system become unavailable. But it's not a bad thing because we know this. We know don't use it. We can alert the user, just don't use it. Even better situations like this. This is our alert limit. Then our potential level is smaller than that. that means your system become available. With this assumption that your PL is smaller than AL, then we can say our PL definitely can fulfill this equation. This is our goal there. That's what we're trying to do. Okay, sounds wonderful, right? Aerospace, they understand all this. But now the question is how to estimate a potential level. Let's do this. So what we're trying to protect, there's a risk. We need to think about what is the risk, where the risk is coming from. So we are doing estimation, position estimation, right? So definitely risk coming from fault. And fault, where we mean is the faulty measurements. You have a measurement that is affected somehow, somewhere, multipass in GNSS, for LiDAR, maybe a dynamic object. So when the fault comes, so there is a risk. So if we have no faulty measurement, there's no risk. But some point, at some time, you gotta have a fault. Living in this real world, you gotta have a fault. So what we have to do is to do fault detection and exclusion to make sure that measurement you use are healthy. This is, I know in robotics they have a different thinking, but this is what aerospace is thinking, right? They gotta detect and exclude. We're gonna using only a healthy one. So the risk is actually become how good you do your fault detection and exclusion. How well you detect your fault and exclude it. And if we didn't do it well, what's the impact? So that become our risk. So in our positioning system, usually work like this. When you have a measurement, then you do fault detection and exclusion, you do positioning, then do navigation, right? Now the key here is measurement and FDE. How do we make sure this is done correctly? And how can we quantify this confidence? This is the key. So let's look at the very simple positioning model. That integrity, we believe the integrity risk is coming from this. Like you have the positioning state you're trying to estimate. You've got a sensor measurement that you receive, and you have the measurement noise, right? So in this particular case, we just easily using a least square. I know it's very typical, but just for the sake, it's simple. So this is our estimate position. And what's your estimate error? You put the measurement error over here. This becomes a measurement error. This is become a positioning error, right? So this is actually become, the magnitude of this is depending on the model itself. The model itself, right? The algorithm model. And the uncertainty of this positioning error coming from here, the measurement noise. So we brought the idea that, very simple, your measurement space using the model edge come in the positioning space. So your measurement uncertainty using the model become the integrity risk. So it's all about measurement. It's all about measurement. Your risk is all about measurement. Now we know the measurement is important. Let's look at how do we do it if we know the measurement is important. Now we have a different measurement, the measurement error. Can we starting to do overbound, which is like bounding? We do the modeling, statistically modeling about how the noise is going. So we try to model the measurement noise distribution to know the error statistic. If we can do this correctly, then because we know the statistic behavior, we can do detecting the fault using a lot of good theory, chi-square, statistic, solution separation, we can do all that. And then we can calculate the position level using the statistic in showing our positioning estimate are within the risk assigned. And after that, we know it's all good. The FDE result mean like the faulty measurement is excluded. We're using positioning, then navigation. Okay, this is how we do integrity monitoring in aerospace. Right, so this has been done for maybe the past 20 years. So aviation sector have been doing this. When you have the aircraft landing to the ground, then you have different phase that define different integrity risk. They do all this. They do it, the GPS positioning, all this already. So this is pretty good for aviation. And they will work because there are two assumptions. The first assumption is we're assuming that it is Gaussian. Everybody loves Gaussian, right? So everything we see here is Gaussian. I'm here to challenge this. Everyone love Gaussian. So it's a known distribution. So it makes our statistical inference easy. You can do fault detection, exclusion, you can do integrity monitoring. Right. So here when we talk about modeling, how do we categorize the measurement error? So this is a PDF. This is the value, this is the probability. So you have the red one, which is the actual, the real noise model that you're trying to model, right? But we cannot just model perfectly, right? What we usually do is we're using a fat Gaussian, much fatter compared to this actual one, the red one, which is one to be bounded. We're using the fat over bounded, the the blue one, trying to overbound it. What do I mean by overbound? So this is the PDF, and this is the CDF cumulative, right? So if, let's look at, we have the extreme value, 0.7, the 2 dashed line over here. If this is extreme value, then what we're trying to say is that, okay, so if this 0.7 period, that this is extreme value, right? So my factor Gaussian has larger probability to reach the extreme value. That means you become more conservative. So now we have a conservative model, right? It's just equation. And after we are conservative Gaussian, then what we do, then what is the next, excuse me. So after we do conservative Gaussian, but we want to look at in real world, what does it look like? In real world, so I'm using one example in satellite navigation, like the satellite clock and orbit actually calculated by the GNS system, right? So the system, the ground station will do all this calculation, come up with the corrections, send it to satellite, and you receive this and you correct all this, all beautiful. But it's not perfect as well. So this is the actual errors that is collected from 2008 and 2015. So how to read this figure? This is the error. This is the error of your correction that you generated. Okay, this is the error. 0 is perfect. So this is the error. Negative and positive. And this is like the probability that this level of error occur. So you see like 0 most of the time, right? So you see when the error go large, then you have very, very little opportunity, probability you will come up. So this is all kind of error of the satellite orbit. But what the field has been doing is like, okay, so I want to bound this. How about just using a fat Gaussian? It's easy. I can bound everything, right? Everything is included. So this is for GPS. And this is for Chinese Beidou. Similar thing. So we also collect from 2016 to, not we, the paper, 2016 to 2020. Bound it. Bam! So good. So good. So just using a fat Gaussian, we all love Gaussian, just using a fat Gaussian, bound it. So, and then you come to urban, you have multipass, right? You can think about this as to be even fatter and fatter, right? So the long tail of the multipass has become crazy. So this is difficult, but I will talk about why this is important, why this is difficult later, yeah? Okay, I'm going to talk about second assumption that we made in integrity monitoring. So the second assumption meaning like the measurement residual is proportional to your estimated error. So what I'm implying here is that there is no local minima. No local minima is allowed it. If there's a local minimum, integrity cannot be done. So if you have to do this, then you need to make sure your linear model is good. Okay? But how do we convert there's no local minima? So FDE, you have to do FDE really well. All detection exclusion, make sure it's all healthy one. Right? So after you have this is a model Gaussian error, right? We already have nominal error here. Then you can do either chi-square test, I won't go into detail, or do the solution separation test. And you can define a certain threshold, get rid of Lowe's measurement, say, oh, so good. Okay? So this is FDE. So after we do this, all the measurements are clean, assuming this is true. Then we started to do the last part, how to compute the partition level. When we want to do partition level, one is the most popular one, is multi-hypothesis solution separations. Again, this is our goal that I've been showing for a long time, right? This is our goal. So what is being done is that we believe the risk is from the measurement, right? So throughout my presentation, I'll talk about this. Risk is come from the measurement. So we're going to have different hypotheses. First, all the measurement here, subset, they pass the FDE are healthy. Okay? And we have the second hypothesis. Out of all the measurement coming to pass the FDE, only one have a problem. Okay? This one have problem, this one have problem, or even two have problem. You can have many hypotheses to see how many fault you have. And then you put this figure into an equation. That means the first part here is that believe all full set are healthy. You still have a risk. Why, when it is all healthy, you still have a risk? Think about Gaussian, right? So in the very long tail, you still have one very, very little chance of coming up with a crazy value, right? So that's doing that. And this is doing that at different measurement. May have the fault, but FD doesn't found. So I don't have an alert here, right? So I have so many different hypotheses. See, like so many hypotheses, I consider all the hypotheses. Then I say it's all good, but I didn't alert. So consider these two very same equations. The red one, blue one add up together. Then you have the integrity risk. Then you need to find out the partition level that is minimize the probability. This is how we do. Right. Now, okay, you know how to calculate partition level. So you know, like, okay, in first phase. So how to do this probability? We only know Gaussian, right? We only know Gaussian. So when this is probability, I can use in Gaussian to write down the probability equation very easily. So that's why Gaussian is important to calculate the partition level. But what's the problem? So here is an example. If this is the real measurement error, okay? So again, this is error, this is probability, this error. So if you have a fake Gaussian here, 0.5, you're trying to bound it, right? So what's the result will be look like? Because it's a fat model. So you're using really fat standard deviation. So you have the fat partition level. And if this is your alone limit, I talk about this. Is it useful? Not really, right? So now our advocate, after 17 minutes, come to my advocate. Our advocate is, can we model the error more tightly? Can we try to model the error more tightly? Not just a Gaussian, using Gaussian mixture model to mix the two Gaussian together and to model, like put that second part, like this is one Gaussian here, another Gaussian here. Can we try to do that so that we can get a tighter partition level that become useful for Vigo application? So that's the whole advocate here, right? So again, so here, Gaussian assumption will limit the system availability. And that's why the aerospace, this integrity monitoring, you want to put it to the urban, you want to put it to Vigo, it's always hard because there's a fake Gaussian there. All right. But why Gaussian? Everybody loves Gaussian, right? So it's when you have an uncorrelated Gaussian variable and they are independent, you can easily do fault detection chi-square test, priority space. That's all been done. And if the linear combination of Gaussian are still Gaussian, right? So when you have a linear model, linear noise, come to the positioning space, it's still Gaussian. Everything become easy. Everybody love it. Yeah. But we are talking about, can we try to embrace that our noise is non-Gaussian? Can we model it better? So what we're trying to say is like, okay, in the Gaussian modeling, can we do more precise error modeling? So we do the non-Gaussian overbound. And after that, if we have a better, the tighter bound, we can improve the detection ability, and we probably can reduce the production level and improve the system availability. That's the goal. So this is the presentation I talked to my student when he joined my team, and this is the student who finished the job and going to show you the result in the next 3 pages. And he's looking for postdoc opportunity. So if you happen to secure a big funding, want someone to work on integrity, he's the good one to recruit. Really, really nice person. Yeah, he can do LiDAR, SLAM as well. Yeah, take that photo. That's what I like. Yeah. Oh, sorry. No. Go ahead. Check that photo. So, yeah. So the following math are super difficult. So to be honest, like we publish in IEEE transactional aerospace that, the student derive a really rigorous model. If you know this journal, like this is the place we publish integrity stuff. So he did that, and he using a principal Gaussian mixture, basically just 2 Gaussians and mixed together, and he can come up with something like this. So this is the result. We talk about overbound here. We're using non-Gaussian to overbound, and he's not comparing with some very old research. He's comparing with a 2-step Gaussian, which is also mixed Gaussian, and published in 2019 and by Hong Bunch. He's really wonderful researcher here. But you can see like the model we proposed, the principal Gaussian, is a bit tighter in this part. And that make the potential level much tighter. You will see that later. Right. So if you're interested in what we talk about here, go Google, go find Hongzhou and find the paper. So basically we propose a non-Gaussian CDF, they overbound the non-Gaussian heavy error type distribution. And this is good because it can translate to position domain. You're going to see later. And after he finished that overbounding, non-Gaussian overbounding over here, he do the FDE, also using the jackknife. Again, that math is difficult. I don't know how to explain. He got a student paper over here, but I'm going to show you the result. So, how to understand this result? So, this is a global map. So in our research field, we use the global map because when you have satellite circle around the Earth, right? So in different locations, you got different satellite geometry. So we're going to look at the different geometry. So in here, he inject non-Gaussian noise into the simulate measurement, right? So this is conventional Gaussian solution separation, which is the one using in aircraft today. And the color here means the detection rate. If there's a fault, because we simulate it, we know there's a fault, right? So how accurate you can detect that. So 50% all the way to 99%. So you see the conventional approach is within 90% to 95%. And you can see this approach because it's designed for non-Gaussian. So it's coming to 99%. Yeah. So this is something that is starting to detect the fault. You can better detect the fault. You can imagine the next part you will see is the potential level going to be tighter. Right. So the contribution that he using the jackknife detector. The jackknife detector, the key idea is that he detect the fault in measurement domain, not in a position domain. A lot of solution separation, they just do in the position domain, but you do in the measurement domain. Okay, the last one. After we do the overbounding, after we do the FDE, then here's the potential level. So we do very similar thing. But the color you see over here is not the detection rate. Now is the partition level that I always calculate the blue circle I talked about in the previous one. Again, is this in scale of PR? Multi-hypothesis and so Gaussian. And their partition level is about 50 meters. And this is about 30 to 35. 15 meter reductions. So I'm not saying that this is good for car, but I'm just advocating that seeing the power of embracing non-Gaussian noise can bring down the partition level. And then you have better opportunity to really net your partition level tight enough to 1.5 meter, which is the holy grail in autonomous driving at this day. So embracing that. That's what we're trying to say. Right. So another contributions. So here comes to my conclusion. I hope I didn't use too much of the time. So we propose a non-Gaussian map overrun, make it more precise error modeling, detect more efficiently. Then we can improve the system availability. That's what we do. So the takeaway is we demonstrate the power of non-Gaussian error modeling. We only demonstrating in some, but this should be done. That's what we're trying to say. One last page. So what's our next future work is that we still have limitation if zero mean. We have zero mean assumption. That means that our nominal model is always zero mean. So whenever you have a bias, it's a fault. So we want to assess some of the bias because sometimes if you are too conservative, say it's always no bias, very hard. So we want to spend on that. Then currently the potential level you see is only a single fault, meaning like out of 20 signals, only one signal is fault. So we want to expand that to like multiple, 3, 4 at the same time and making the computation level going down. But that's a lot of work. Right. So finally, I want to say like this is the challenge for our community because I'm presenting in this workshop. I still need to do something relevant. So I believe that sensor fusion based navigation is definitely the way for robotics, right? So how do we quantify the integrity of a LiDAR camera using what I just mentioned? So what I mentioned is just a framework. I didn't talk about what positioning management, what model I use. It's just a framework. So maybe we can try to do this integrity for LiDAR. So LiDAR slant, LiDAR mapping, maybe we can start to do that. How do we quantify this risk, right? And should we do the partition level for LiDAR itself, partition level for GNS itself, or we join together? A lot of questions need to be answered. With that, thank you for your attention.
Thank you, Dr. Xu, for your insightful presentation. Any question?
Daniel?
I got that you bring up.
Somebody's not happy. Oh yeah, so you have to come here. Yeah, you are not as loud as me. So. Yeah.
Yeah. I mean, you were talking about this lack of assumption of the Gaussian distribution.
Yeah. Yes.
But then when you are targeting non-Gaussian, but do you have a particular assumption on what's the target distribution that you want to address?
Yes.
Or is it something more flexible in the sense that?
Okay. So the question is like, do I have a specific type of model that used to model non-Gaussian? Yeah. So we work with Tim Pfeiffer. So he is the one who brought up with the GNN using FGO. You kind of like real time, like tune the sigma mean of the GNN, right?
Rosen is technical.
So our advocate is binary Gaussian mixed model. But maybe David, you have a better idea. So I believe binary is good enough for most of the case. I hope. And this, for our perspective, it's easier mathematically derived. If you make it like infinite number of that, oh my God,
So finally make it a bit easier for us. Yeah.
Because that was the second question, because you say that you have this fault detection and exclusion mechanism, and you are already saying that this is complicated when you have multiple faults.
Yes.
And what about you don't detect and you do not exclude? Is there any other framework that could relax this thing, such as you never...
Daniel is spoon-feeding me. He's talking about the robust estimation, right? Yes. So I'm thinking about that too. So that's why I think it's very important the two community talk. Because, you know, like when we do the fault detection and exclusion, we try different subsets. And there's crazy amount of computation law. And we also talk about this. You have to design the real-time code, and what signal is coming, what signal is coming out, and so hard. If we can just using outlier and just get rid of that. But how do we quantify the risk from the robust estimator? That's the question we'll be asked if you submit journal to the journal I submitted to. But I believe that's the direction. Thank you, Daniel.
No.
Perfect. Thank you. Any more questions? Do we still have time? Maybe just one?
Just like last question. So, Dutch go back to one slide showing like the linearization part. So
okay.
Actually, I just have one question. So, I think it's very clear that for the GPS problem, okay, it's like more like linear problem.
Yeah.
So I think for example, like if we look into the problems like we have very complex like post estimation with orientation stuff and also with highly non-complex measurements like highly nonlinear measurements like the Doppler measurement as I mentioned.
Yeah.
So if the problem is like kind of non-complex, so I know we can have some solutions. So this question also goes to today. Do you think like is 100%? So what I want to mean is that sort of non-complexity can also lead to the risk to the system. So according to the theory of so I mean, so if you know this problem is non-convex, so based on the existing solution, so if that means you get 100% to quantify, you already get a global solution like this EPL, or still we need to quantify the potential risks maybe coming from the non-convexity like 0.1% of risk, or it's like no risk, or it's still some risk.
Yeah, this is a long question. So, I don't know. So, Dave, what do you?
I mean, just from computation wise standpoints, should expect the games guarantee. I mean, what's the people's theory of quantum computers can solve all problems?
Yes.
But
Yes.
So I think like.
Yeah. I think it's complementary rather than conflicting. Yeah. Just a quick comments to when you have a model which is highly nonlinear. So I suggest that we provide better initial guess in the predicals. I'm talking about predical applications, but this could be hard in some application. But if you look at for vehicle navigations or some like more mature market, maybe we can do that, right? Just find a way to provide. But for me, the safety is more important than the accuracy now. So I believe that. So we should try our best to provide good initial guess. Make sure your model is easier to get linearized to the right place, so you get all the convexity probability. Yeah, thank you. So I guess I used too much of time. Thank you, everyone.
Yeah, thanks very much for the invitation to speak. This is a super cool lineup of speakers that I think there's already been some very interesting discussion, which hopefully will be continued later in the day. So so I'm going to talk today about certifiably correct perception, which is probably the work that my group is best known for and which we've been working on for a while now, and I think is hopefully will be particularly interesting to this audience. So the motivation behind this work is, my group mostly works on problems in robotics, and one operationalization of that is that robotics is the science of physically embodied autonomous agents. And so if we think about the kinds of problems that are associated with physical embodiment, the things we want robots to be able to do involve core capabilities involving like planning, navigation, and manipulation, really all require accurate models of the environment around the vehicle in order to carry out these core functions. And so, as an example of this, let's say that might be of particular interest to people interested in transportation systems. If we consider the case of like an autonomous vehicle, and we look at like an autonomous car's eye view of the world, the main thing I want to point out here basically is this is the internal model that like an autonomous car has as it's driving down the street. And so if you think about what are the kinds of models or what are the things this vehicle needs to be able to do to drive safely? Well, it's got to estimate where it is on the road, where other vehicles are around it, where are the safe lanes to travel in. Detect stop signs and so on. What are safe maneuvers that it can make? When does it have to approach a stop line and so forth, right? So the punchline here is, there's a bunch of stuff that's going on, and all this stuff has to be estimated, and it's all going to be estimated correctly, because if you misclassify a stop sign as like a 50-mile-an-hour sign or something like that, and there's like a bunch of school kids around, it's going to be like really bad. It's going to be really, really bad, right? And so take this, multiply all these decisions that have to be made on an ongoing basis by all the vehicles that are on the road, and the level of reliability that is required in these estimation systems, to have these vehicles operating safely is really high, really, really high. Okay, so how are we going to solve this problem then? Okay, well, so, I've used this word perception now, and, really what I mean by that is anything that sits between raw sensor data and, basically perception is a box that takes in raw sensory inputs and outputs some model of the world that we're then going to use for downstream planning or decision making. And there's many different ways to formulate such problems, but the punchline basically is if you crack open any paper or book on perception in robotics or computer vision, you're almost certainly going to see a formulation that looks like this. So it's going to be an optimization based problem, where the idea basically is we have some parameter that we want to estimate, which let's call it theta, and this could be position, orientation of your vehicle, velocity, positions of pedestrians, and so on. There's going to be some data that comes off of your sensors. And there's going to be some loss function that basically is going to measure the discrepancy between, the data that you got and some guess that you might have for what the solution is. And we're going to then generate an estimate by finding the estimate that best agrees with our available data according to this notion of discrepancies. That is, we're going to solve an optimization problem. Okay, so, maximum likelihood estimation does this, robust estimation does this, empirical regularized risk minimization and machine learning does this, right? So all these things are based on the same sort of underlying optimization-based principle. Okay, so what's the problem then, right? Well, the problem is that if you read these papers, this is about as far as they get. They'll write, they'll say something like, okay, this is the optimization problem that you have to solve, and if you can solve that optimization problem, then you're good to go. What they don't talk about is, okay, but for real, how are we actually supposed to do this, right? And so this is problematic because if you look at sort of any real world example of these problems, these are almost always high dimensional, in part because there's a lot of states to estimate, right? So imagine, setting all the, having to decide what are all the weights going to be in my neural network, for example, right? You saw how many states were being estimated in those autonomous car problems as well, right? Typically, there's a lot of states that you have to estimate. So that's problem number one. And problem number two is that the actual, both the domain and the objective functions that appear in these problems are almost always non-convex as well, right? So case in point, instead of, one of the things that I'm especially interested in for robotics is like, where are things in space, right? And literally the orientation estimates that form part of that answer are themselves a non-convex parameter space. So like anytime you're talking about orientations, anytime those appear in your problem, you're already talking about a non-convex optimization task. So this has important practical implications because anytime you see both high dimensionality and non-convexity, there should be like alarm bells going off in your head because those problems are almost always computationally hard in the sense of computational complexity theory, meaning they're NP hard in general to compute. And operationally, the way that this manifests in application is through the presence of many, many bad local minima that can entrap the optimization techniques that are typically applied in practice to solve these estimation tasks. Okay. So just as an example, what I'm showing you here is a trajectory estimation or mapping task that is from real data. This is taken by the Stanford autonomous car. And in this particular application, this car is going to drive through this parking garage. So it starts down here in this parking lot, it drives through this parking garage, and then up and down the ramps, and then back outside again. And if I were to generate the corresponding instance of one of these optimization problems to model this trajectory estimation task, and I were to show you the actual, honest-to-God, globally optimal solution for this problem, the true answer, it looks like this. And this kind of makes sense. I mean, you can see here, these are the ramps. This is the trajectory to and from the parking lot and so on. It looks pretty good, right? Okay. What would happen if I just picked a bad starting point and I just went downhill and did local search in the usual way when solving a problem like this? Well, these are the kinds of things that you can get, right? So that's pretty bad. I invite you to try imagining driving your autonomous car at 150 miles an hour down the Autobahn using a solution like this as the basis for your navigation and decision making, right? That's not good. It's like not good. And this is how most existing state estimation systems in robotics are built today. So when you have autonomous cars that are on the road now, this is actually what they're doing under the hood. Okay, so the main question that motivates our groups, a lot of our groups' work over the past several years has been, is it possible to develop estimation methods that are both tractable, that is, we can run them in real time on resource-limited mobile platforms, but that also allow us to say something strong about the kinds of solutions that we're going to get. That is, can we somehow get both computational speed and also guaranteed reliability out of estimation procedures like this? Okay, so the main idea that I want to talk to you about today is how we can do that. So the main idea that's motivated a lot of our recent work is that convex relaxation provides a powerful approach for building fast and global optimization methods that are capable of solving a lot of these challenging machine perception problems in practice. So in particular, if you're sufficiently clever about how you design these things, these enable the recovery of provably globally optimal solutions under realistic problems. And if you're clever about how you design the underlying optimization methods, these actually can also be done as fast, or in some cases faster than, existing local, heuristic local search-based techniques that comprise sort of the current state-of-the-art for building these systems. So altogether, what this gives us then is a principled and practical approach to solving robust machine perception problems in practice. Okay, so what I want to just quickly describe today for you then, I'm going to use robotic mapping as sort of and specifically PostGraphSlam as sort of a concrete example to illustrate how these things work. So what we're going to do then is I'll just give you a quick lightning recap of PostGraphSlam in case some folks here may not be familiar with that. And then I'll tell you how we can design robust estimators to solve that problem in practice in that specific case. And then I'll finish up with some generalizations of this construction, some open problems, and some current and future research directions. Okay, so real quick, lightning introduction to the robotic mapping problem. Let's suppose that we've got some robot and we want this robot to, be released into some environment, like hypothetically the Expo Center at Northeastern, and, drive around and construct some map. So the basic idea, in terms of mathematical modeling, we're gonna model this problem using a gadget called a postgraph. And the basic idea here is that this robot is going to start at some initial position. And as it drives around and explores, it's going to move through some sequence of poses, that is, positions and orientations in space. And depending upon what kind of sensors it has on board, we can do things like odometry estimation via, inertial integration, or laser scan matching, or visual odometry. And what those measurements give us is they directly give us estimates of how our vehicle has moved between subsequent poses. So this gives us sort of like, sequential trajectory estimates. But if I then go around, some loop and come back to a place that I've been before, I might be able to do something like place recognition that will allow me to estimate my position now relative to somewhere that I've been in the past. And so the overall picture then is that, as this robot's moving around, we can generate this graph, this network, that contains in it, as vertices, the positions and orientations of the robot that we would like to estimate to know where we've been. And we would like to estimate these unknown positions and orientations based on these estimated noisy transformations between these poses that we can generate using our onboard sensors. Okay, so the formalization of this mapping task then is something called PostGraphSlam. And the problem setup is as follows. So we're going to be given some collection of n unknown poses, that is, positions and orientations in space, and a collection of noisy pairwise relative measurements of how we've moved between certain pairs of these poses. And what we want then is we want to figure out, what is the best estimate for the joint estimate for this entire trajectory that my robot has traversed through, given these relative pairwise noisy measurements. And so under some suitable noise model, which I'm going to dispense with, but just take my word for it, under some suitable noise model, it is possible to formulate this problem as a maximum likelihood estimation that looks like this. So the punchline here basically is, the way to read this basically is, there are two terms here, which basically correspond to, how well do my estimates model my agree with my rotational motion and my translational motion. So for each measurement here corresponds to one of these sum ends. And each of these terms models basically how well my endpoints agree with the measured relative motion, rotational motion, and translational motion. And so these scalars here, kappa and tau, you should think of as being precision parameters that quantify how accurate each of these individual measurements is that contributes to this sum. Okay, so the punchline here is, this is a nice, sum of squares objective, so that's great. But because I'm doing estimation over poses, and these poses in particular contain orientations, this parameter set is actually non-convex. And this is going to be a high-dimensional problem as well, because there's just a lot of poses that you need to go through to map a large building like that eccentric like I mentioned. And so this in particular is a high-dimensional non-convex problem, and so it's NP hard. Okay, so it's hard to solve. On the other hand, it's also a particularly useful problem to be able to solve because, perhaps unsurprisingly, as you could probably imagine from that setup, this problem occurs ubiquitously throughout geometric estimation. So it occurs as a problem in robotic mapping. It's a subproblem in 3D visual reconstruction. It's used for multi-sensor rig calibration, which I think Matt will talk about later today. So it's hard, but it's also mathematically interesting, and it's also super useful in application. So if we could solve this, it would actually be sort of like a useful thing to be able to do. Okay, so given everything that I've told you, how are we actually going to go about solving this problem then? Okay, so the main idea that I want to convey is that we're going to use convex relaxation. And in particular, we're going to use convex outer approximation in order to do this. Okay, so the main idea here is, we shouldn't expect that we can efficiently solve NP hard problems in general. But the word in general is doing a lot of work in that statement, because all that means is that if you think about what NP hardness means, if you give me a problem class and an algorithm that you claim can solve every instance in that problem class, all that means is that I can go into this problem space and I can pluck out one or a couple of examples that have to make your algorithm work super hard, doing something like, exhaustive search over an exponentially large search space. But it doesn't say anything about how prevalent those hard cases are. And so pictorially, what we might hope is that perhaps there is a separation notionally between super hard cases that make this overall class of problems hard and the kinds of problems that would show up in real world applications that I care about solving. And there's maybe some rational basis for having this hope, which is to observe that, so maybe what this would let us do is perhaps we can think about well approximating at least the reasonable instances of this problem. And maybe one reason to believe that this is not a crazy notion to hope for is that it turns out a lot of animals have to solve similar kinds of mapping and navigation tasks to what robots do. And I, as a human, I'm not like regularly walking into walls and stuff, right? I mean, like occasionally, but not usually, right? And so what this means then is that at least, there seems to be some empirical evidence that a lot of the problems that show up in real life maybe are not as hard as this worst case adversarial notion would suggest. So maybe there's some reason for hope. Okay, so then you might say, okay, well, that's great. That's a nice story, Dave. But then, how do I take that intuitive notion and then actually do something useful with it, computationally, right? How do I operationalize this idea? So the main idea that we're going to use is, in order to operationalize this approach, is we're going to use convex relaxation. So that is, we're going to show how you can construct a convex approximation for these classes that we can then solve as a surrogate for our original difficult non-convex problem. And so this is useful because there is some standard machinery for constructing these via outer approximation, Lagrangian duality, and so on. And because convex problems are a lot easier to analyze than non-convex ones, not only can we get some nice approximations, but in many instances we can actually analyze these approximations in a way that allows us to conclude strong statements about the quality of the estimates that they will return. Okay, so that's the general picture. How are we going to use this to solve postgraph SLAM in particular? So I'm going to show you two steps to do this for this particular example. So first thing we're going to do is, here was our nice MLE. First thing we're going to do is we're going to apply a real quick simplification of this to get a nicer version of this problem. And the way that we're going to do that is just by observing that if we were to fix an estimate for the rotational states, the estimation task in the remaining translations just reduces to an ordinary least squares problem. And we know how to solve those using linear algebra. And so the punchline here is that because of that, we can actually construct an analytical solution for these translations as a function of rotational states. That is, once you tell me what the rotations are, I can immediately tell you what the corresponding optimal choices of the translations have to be. And it turns out that relation is a linear relation, because it's just based on matrix factorizations. And so what that allows us to do is we can then take this optimal assignment, substitute it back into our original problem. And the effect of that is that it allows us to analytically eliminate these translational states from the problem. So what we get then is a simplification, an equivalent but simplified version of this problem, which can be written in this way. where Q is a data matrix, and the only variables of estimation that are left are just these rotations, which I've stacked into a row matrix, a block row matrix. Okay, so that's simplification one. Simplification two is, this is the main step. Now I'm going to show you how to construct a convex relaxation for this specific problem. Okay, so the main thing to observe here is that the only way that these rotations enter this problem now is through this outer product, this symmetric outer product. And if we say, okay, what does that symmetric outer product actually look like? Well, first off, it's going to be positive semi-definite because it's a symmetric outer product. And because these are row matrices of rotations, and R transpose R is the identity for any rotation, this matrix is going to have the identities along its identity matrices along its block diagonal. Okay, but now if I ignore this left-hand side and I just look at the right-hand side now, right? So that means basically every one of these R transpose R's is going to be a positive semi-definite matrix with this identity block diagonal structure. But if I ignore this guy and just look at this set on the right, this is the intersection of a set of positive semi-definite matrices with a set of linear constraints. That's a convex set called a spectrohedron. And so basically what this tells me is that, you know, these things are complicated. These things are relatively simple. It's a convex set. And so if I think about just replacing, literally just replacing R transpose R with just a generic positive semi-definite matrix that has this prescribed block diagonal, the thing on the right is actually a convex approximation, an outer approximation of the thing on the left. Because every one of these guys is a matrix that looks like this. So I can think of this as a convex relaxation or an outer approximation that's gotten by expanding the feasible sets of my original maximum likelihood estimation. Okay, so what does this get me? What does this get me? It gets me two main things. So first off, I can immediately conclude that whatever this optimal value is for this problem, it's a lower bound on the optimal value of this problem because I'm minimizing the same objective over a larger set, and so I'm always going to be able to do just as well. So that's immediate. Second thing it gets me is, if I were to solve this problem, and it so happens that this minimizer that I get admits a factorization in the form R transpose R, where R, you know, is a block row matrix that has rotation matrices in its blocks, then I can immediately conclude that this R is actually a globally optimal solution for my original problem because it attains this lower bound on the optimal value of my original MLE. And so you might say, okay, that's great. That's like a cool result, but like, you know, given that we have a bunch of extra stuff in here that doesn't correspond to these guys, why would I ever expect this to happen? And so the main result that we actually derive in this work is to actually show that it does. So in fact, like this actually does happen in like real life. This actually does occur. So the main theorem that we prove, and I'll sort of, this is a lot of math, but I'll walk you through it. The main idea here is basically, if we were to consider this, the ground truth matrix that was constructed from noiseless data. So this is the ground truth relative to motions. Then there's some constant, which is a function of this matrix, such that as long as my data matrix is not too far away from the noiseless ground truth, so the data matrix constructed with the ground truth values, then this semi-definite relaxation has a unique solution Z star, and that unique solution factors in exactly the way that I require in order to get a globally optimal solution to my original problem. So the punchline here is, really what this says intuitively is, as long as the data that's on my, as long as the noise that's on my data is not too large, I can solve this STP, and the solution to that STP will give me a globally optimal low rank factor for my original maximum likelihood estimation. Okay, so we can take this and then turn it into an algorithm. And the basic idea behind this is, it actually leads to a very simple algorithm called SASync. And all we do is we're just going to solve this STP. We're going to take that solution and we're going to extract a low rank factor of rank D from that solution using just a singular value decomposition or eigendecomposition. And we're going to return that estimate together with the lower bound that comes from the optimal value of this STP. And what that theorem says is that in the event that the noise on my data is not too big, that R that I can compute will be a globally optimal solution for my problem. And if I simply check the value of that estimate in my original problem, if this value turns out to be the same as this lower bound, then this certifies that R is optimal. So not only do I get an optimal solution, but I know that I've gotten an optimal solution. Or conversely, in the event that this doesn't hold, I know that the noise on my data was too large, and therefore I can conclude that I'm unsure as to whether or not the answer is correct. So this gives me the ability to not only compute estimates reliably, but also verify their correctness after the fact, so that our robots have a kind of introspection, which is a particularly nice feature of this. Okay, so far I've shown you how to derive these convex relaxations. We've proved this is exact for bounded noise. So then the question is like, okay, so does it blend, right? Like, does this actually work in real life, right? So what I'm going to show you here is an actual simulation of what this looks like in a real example. So I'm going to show you, starting from a bad initial guess, I'm going to show you what GTSAM would do, doing local search on the left here. And you can see that, perhaps unsurprisingly, this local search method is really kind of struggling to figure out how to disentangle this bad initial estimate for a graph here. So now what I'm going to show you on the right is, so keep in mind, we're solving some high-dimensional convex relaxation of this. So what I'm going to show you is the low-dimensional projections of this high-dimensional state that this convex relaxation is optimizing as it's moving through this higher-dimensional lifted space. So this is starting from that same bad initial configuration. But the punchline here basically is that because we're solving a relaxation which has no local minima in it, we can actually move through this higher-dimensional relaxed space to disentangle this map by passing through these higher dimensional degrees of freedom that don't exist in our original problem in a way that allows us to actually unfold this into a nice, correct solution. So I don't know, for those of you who maybe have not worked with SLAM before, you should be very impressed. I don't know, I thought this looked pretty much like magic the first time that I saw it. So these, they're pretty cool. So at least I think anyway. Obviously I'm biased, but I think they're pretty cool. So, okay. So quantitatively, what does this look like then? So what I'm showing you here are some large-scale SLAM benchmarks that are typically used to evaluate the performance of SLAM techniques. And the main thing to take away from this is that, we can compare, like I said, the objective value for the estimate that we get with this lower bound. And that gives us a way of quantifying the suboptimality of a given estimate that we recover from this approach. So the point to notice here is that, these are real-world examples, or they include large-scale real-world examples, and essentially we get relative suboptimalities that are essentially numerically zero for all of them. So that is, we are in fact solving, getting verifiably globally optimal solutions from these examples that are real-world examples. These are fairly large-scale ones, so these are large enough that these would be considered, reasonable, reasonably large maps. So it's large enough for practical application. And we can do this in a time that is relevant for, resource-limited robotic platforms that have to operate in part real time. So it is a practically effective technique. Okay, so what have we done then? Okay, so we've shown that we can produce a certifiably correct algorithm for postgraph SLAM, which recovers globally optimal estimates for moderate noise, up to roughly speaking 10x the amount of noise that we would expect to see on typical robotic sensors. And we can do this, actually faster than GTSAM if you're clever about how you set up the optimization by exploiting some problem-specific geometry. Fun fact, this is actually the first algorithm to appear in the literature that was provably capable of recovering correct algorithm solutions to at least postgraph SLAM anyway. So that was kind of neat. And if that had been it, I think that would have been kind of a nice result. But the real reason that I'm excited about this work is not just because we can solve postgraph optimization, but because I see this as really being a proof of concept for a much broader class of techniques for generating many different certifiable estimation methods. And I'll just show you really quickly just what that looks like with one or two slides. If you recall how we got this, how we arrived at this, the basic step that we did was we replaced outer products that look like this with general positive semi-definite matrices that look like that. And that was sort of the key step in this relaxation. But the key thing to note here is that this relaxation can actually be applied to really any polynomial function via a technique called moment relaxation. And the basic idea here for what this looks like is if you give me any polynomial of degree d, I could write it as a linear combination of powers of x that look like this. These are just the coefficients. And so if I take powers that are up to half the degree of the power of my polynomial, I can basically, any polynomial of this form, I can write as a quadratic outer product for some matrix of coefficients C. And this is just purely bookkeeping. It's just purely algebra. If you give me these coefficients C, I can give you back the matrix C that lets me write my polynomial in this way. And then I can do that same trick that I did before where I just, treat this as a trace. I apply the cyclic property of the trace and I can move these coefficient vectors to the right-hand side as an outer product. And so if you stare at this for a second, what you might recognize is that this is exactly the same thing that we saw before. And so I can do the same trick where I just replace this with just a generic positive semi-definite matrix X. And what that gets me then is a way of taking any polynomial optimization problem and transforming it into a corresponding semi-definite relaxation. Purely through algebraic manipulations. Okay, so subsequent to our initial, sort of derivation of this SE sync method, suddenly like a bunch of folks have sort of taken this idea up and started applying this to a bunch of different problems. And sort of this is sort of now, at least in robotics, sort of becoming the gold standard for robust perception in robotic and computer vision estimation methods. So just a couple of ones that I would mention. Matt has some very nice work on sensor calibration he's going to be talking about later, but we've also done some stuff on decentralized and multi-agent SLAM with Yu and Tian. We have some recent work on range-aided SLAM. This is a joint project with some folks at MIT that might be interesting to folks that work on GNSS stuff, which I'd be very happy to talk about later. Okay, so I think in the interest of time, I might finish here. Here are some examples of this. I would encourage you to maybe look up some of these papers on your own or ask me about them later, I guess. Just in the interest of time. Maybe I just wanted to say a couple of words about some current research frontiers then. So given everything I've said, what are sort of the outstanding problems? Whole laundry list of stuff, solving these STPs can be very expensive, so we're very interested in coming up with more scalable STP methods. Conversely, are there maybe more ways to write down simpler convex relaxations that would be easier to work with? Can we get explicit a priori performance guarantees versus the a posteriori ones that I sort of mentioned in the talk? Can we do certifiable approximate full posterior estimation as opposed to point estimation? And then finally, this is like the big one, how do we sort of take these certifiable methods and somehow combine them with like learned perceptual elements, like what you would get from machine learning systems and so on? So if any of this stuff was appealing to you, I might just also mention that we have a recent survey article that talks about a lot of this stuff. This is available on my website. I would encourage you to take a look at it if you like. Okay. Pause for photos, I guess, yeah. Yeah, all this stuff's available online, though, so. Okay, so main takeaways then, so convex relaxation is great. I talked about SE sync in this talk, but, there's lots of open research questions, that whole laundry list that I just gave you. And, of course, all this information is available on my website. And then final thing I would just mention is, we are always looking for strong collaborators, strong students, strong postdocs. So if you have, stuff that you think our stuff might be interesting to work on, or you have any students that you would like, or postdocs, candidates potentially that you'd like to send our way, please do send me an email. I'd be delighted to chat. And again, thanks for the invitation to speak, and I'd be happy to take your questions.
Thank you so much for your such excellent presentation. Does anyone have questions?
Thank you very much for the topic. I was not aware of this crazy stuff. It's very interesting.
Yeah, so I was not aware of this really nice relaxation, and I find it very interesting. How does this sit with respect to, let's say, the more conventional light theory-based estimators of such type of problem?
Okay, yeah, so you're saying Lee theory? Or?
Yeah.
Okay, yeah. So, So these can be sort of integrated together. So, for example, so one way of thinking about this is, this actual problem that we write down, right? Gotta go way back here. Yeah. So I mean, so these are sort of they're definitely compatible, is the way to say it, right? Because this is a Lie group, right? So I mean, we are doing estimation over a Lie group in the usual way. The only difference is that if you open, let's say, Professor Barfoot's book on robot state estimation, the usual noise model that you will see. The usual noise model that you will see there assumes that your noise model, when you're doing estimation over a Lie group, is gotten as an exponentiated Gaussian distribution. Yeah. And sort of the convenience of that is that, people like Gaussians, right? Lie groups are non-Euclidean manifolds. So in general, what that construction lets you do is it lets you essentially adapt a Gaussian noise model to the Lie group setting by defining it on the tangent space and then assuming you have an exponentiated perturbation, right? And so that's nice in terms of sort of allowing us to use the familiar Gaussian models, but it doesn't lend itself to an objective that is polynomial, right? So the key thing that we need basically in order to apply these relaxation methods, we need to apply them to polynomial optimization methods. So what distinguishes the MLE that we write down here from the usual sort of exponentiated Gaussian model is that this is not based on a model of that type. The noise model that we assume here for the rotations is an isotropic Langevin model which is a maximum entropy distribution that is defined just directly on the underlying manifold of SOD. So maybe the broader point is this is compatible with the usual least theoretic machinery, but the difference is that there's no reason to believe that an exponentiated Gaussian noise model is actually the correct noise model for the problem that you have anyway. And so, all models are wrong, some models are useful. It is often useful to be able to, what we've usually found is that it's not too hard to take the problem you want to solve and find an equivalent or nearly so equivalent formulation as a pop that would then allow you to apply this machinery, is maybe the way to say it. Sorry, that was a very long way to answer your question.
No, but it was very nice and interesting. I was also going to say that it reminds me a lot. I think you know this Bava's problem. You know this Bava's problem for the orientation.
Oh yes, yeah. So yeah, exactly, yeah.
And one of the first, like this Davenport solution, that was exactly following the same tool that you proposed on decomposing the problem with this trace of these multiplicative matrices. Just to say. Wait.
Yeah, thanks.
Sit down.
And for the question?
So, great talk.
Thanks.
So, I guess one point I don't understand. So, like, when the noise is too big.
Yeah.
So, like, maybe the next page, right?
A couple pages here, yeah.
Case, you talk about the hot case, right?
Oh, yes. So if the noise is too large, yeah.
Yeah, why hot case get destroyed? The convexity of the product.
So it doesn't destroy the convexity. So maybe the way to look at it is it doesn't destroy the convexity. But what this theorem requires, so in order for what this theorem is really saying is, what we want to get out of this is a solution that looks like this, right? So R is going to be this low rank factorization that has these nice rotation matrices in the row form, right? But we got this problem by sort of by expanding the feasible set, right? So there's a bunch of stuff in this feasible set over here that doesn't look like this. It doesn't correspond to lips of feasible points, right? And so what the theorem is really guaranteeing is that under certain conditions, if we solve this problem, we get one of these points that corresponds to a lifted embedding of a feasible point for our original problem. And so that's kind of what we're depending upon. The reason that can't happen in general, one way of understanding that is for reasons of computational complexity theory. So as I mentioned before, this problem is actually NP-hard. You can write down like NP-hard instances of this pretty easily. And so you shouldn't expect that we'll be able to solve the thing on the right, because you shouldn't expect that a solution of this will always give you a solution of this, because this is polynomial time and this is not, right? So, yeah.
So in short, like, if when I solve the problem on the right hand side, if I didn't see like equals to the condition 2, then I can easily know. You would know, because when you try to factor this, what you will find is that it doesn't have the correct rank, right? It'll have rank higher than this usually, right? So you won't necessarily get the answer, but you can always reproject it onto the feasible set, so you can get at least a feasible point. So you'll always get a feasible point. You always get a lower bound, which is always valid. And you can distinguish whether or not this approach has given you a globally optimal answer or not. So you might not get a globally optimal answer, but you'll know you have it, right? Or conversely, you'll know you have if you get lucky, right? So I don't need to know how large my noise is. I just look at this.
You can just run it. Yeah, you can just close your eyes, just run it, and then like.
Application, just put it and see how it works on the reg.
Yeah, and then just see what you get after the fact. Yeah. Yeah.
Last question. So, okay, let's talk again. I learned from slide many times. Can I go back to page 17? Okay.
7.
Also for this test.
Oh, you said 17 or 17? Okay.
So
yes.
So in here, okay, you provide almost zero initial guess for all the states.
Yeah. Yeah, I literally just randomly sampled this, yeah.
Okay, so I also, this is powerful because one thing I think I need to learn from your collaboration is that, so currently we are talking about problems like initialization, for example, like body frame, the camera, and LiDAR, we need to do calibration, okay?
Yeah.
Also for the GPS, okay, it's in the global frame, maybe from the global frame, like ECF stuff. So also, for the body sensors, like usually from body frames, of course they have differences. Okay, this is the difference between the global and local. So for those cases, we may have no knowledge about the differences. So this is the case. So previously, I'm always thinking about for the whole estimation, you may have some initial guess, but the problem I mentioned just now, okay, in real case and in practice, you have no knowledge about the initial guess for the intrinsics.
Yeah.
So I think this can be a good points to. So we are trying this. For example, like, so have you already tried the calibration cases with your algorithm?
So I haven't done the calibration Matt has, so that's maybe a good segue to his talk. One thing I would just mention is one of the reasons that we were especially interested in this is which is similar.
Yeah, it's also, for example, like for different agents, you have no knowledge about what is.
Yeah. So you can imagine, for example, if you're doing multi-agent stuff, right? If you're doing multi-agent stuff and your robots don't know the relative positions between them, the first time they meet, they're exactly in that situation. So it's not calibration, but it's multi-agent stuff. So in fact, we have, in collaboration with Yuan Tian at MIT, who's the lead author on this, shown how you can extend this SE-sync method to the case of multi-agent distributed postgraph optimization. And it was in part inspired by that exact question. So if you have agents that are meeting for the first time and they don't have a good initial guess for the relative frame transformations, how do you solve that problem, right? So yeah, turns out we can do that with this as well, yeah.
Okay, yeah, it's just one more follow-up question. Can we go back to the basis? So because Tosh mentioned it's mainly a question for like, so for this comparison between GDSense and the specific, okay, also learn from this package, this package. So in this test, so for each relative measurement between the post A and post B, so the variance is fixed value for all those measurements.
I think in this particular data set it was, but it doesn't have to be. So if you look at our actual, if you look at the actual sort of model that we start with here, right? Yeah. So there's no assumption the measurements here have to be, like say IID, right? I mean, you can easily have just heterogeneous variances, let's say, in these measurements. Yeah.
Yeah. So the next question about, so for example, the GD set. So you do this comparison between the results and the one is from GD set, the one is from the sync, okay?
Yeah.
So, for example, the connection load is almost the same load. I mean.
So our method is actually faster than GDSAM for this specific problem, but that's because we do a bunch of fancy stuff that I'm not talking about here. Maybe this is one thing that I should mention, perhaps, right? One of the things that makes this stuff difficult is that the STPs that you have to solve in order to do this are pretty large. So if we solve this reduced problem and there are like 15,000 poses, let's say, right? Each of those contributes a block of size 3 in the 3D case, right? So this is going to be an STP that's on the order of, let's say, 45,000, 50,000 dimensions. Your decision variable is going to be a matrix that's dense of size like 50,000 by 50,000, right? If you try to instantiate that in memory, it will crash your computer. So I didn't talk about this at all in this talk, but a big challenge in getting these techniques to work practically is to figure out how you're going to solve large-scale STPs, not just fast, but like at all, right? I mean, first at all and then fast, right? So a big chunk of this work that I just didn't have time to speak about was how do you, now that we know this relaxation is good, how do you then design optimization techniques to solve it efficiently in practice? So that involves a bunch of structure exploitation and exploiting the underlying geometry and so on. But one of the payoffs for doing that additional work is not only can you solve the problem, but that actually, if you're very clever about how you set up the optimization, you can actually do it super fast, actually, in fact. So the actual method that we end up with is actually faster than GTSAM when applied to the specific problem of PGO, because we heavily exploit the geometry of that specific problem to design our optimization techniques.
Thank you for such great work.
Yeah, thank you.
Thank you for the kind introduction and for inviting me with this stellar lineup of speakers. Today we're going to talk about two closely related problems that I think are relevant to this research community of intelligent transportation systems that I've studied from a robotics sort of lens. Let me just see, is there a full screen mode? Oh, full screen mode, there you go, yeah. Sorry, I just missed it. Okay, yeah, that's good. Okay, so let me introduce the problem. Accurate localization on the scale of cities requires fusion of information from a lot of sensors. So this is just a view from the AutoCalib papers data set of sort of one nice long view of a street, and you can imagine hundreds or thousands of streets of this size intersecting in a metropolis. And that is a ton of data, it's a ton of sensors, it's a ton of cars and objects being measured. And we need to understand where these sensors are in two senses of the term where. So let's look at this. So the topic today is where are the sensors? And the first approach is sort of where should we place the sensors? So if we're in charge, we're designing infrastructure. where should we place sensors and even fiducial markers. So in robotics, we use April tags a lot. So things that cameras or other sensors can reliably detect and use to localize or build maps or as part of some sort of localization and mapping solution. So this is a design problem. The second problem is that once we've placed these sensors, or if we're given some scenario where a lot of the cameras and other sensors and markers are already built, so you've got infrastructure, how do we accurately calibrate the poses? So this is extrinsic calibration. It's not the intrinsic parameters of, say, a camera. It's the relative pose of all these sensors in an environment. So both of these are sort of versions of the question, where are the sensors? The first one's more, where should the sensors be? But that's what today's talk is about. I'm going to kind of sandwich in these two topics because I think they're closely related. And our answer to both these questions will involve convex optimization. So credit due to the organizers today for ordering the talks in a way I get to sort of springboard off Dave's excellent mathematical background and basically quickly go over a lot of the convex optimization stuff at a higher level. So I appreciate that. Briefly though, just to remind everyone in case it was your first exposure in Dave's talk, we have this idea of non-convex problems that have local minima present. So here's a one-dimensional example. And this non-convex function, f of x, has these harmful local minima we want to avoid. So we might, for example, have a surrogate convex relaxation f hat of x in green here. And for functions, convex, at least in 2 and 3D, means like bowl-shaped, right? So it means the local minima are all global minima. And ideally, we want the global minimum of f hat of x, our convex relaxation, to be the same as the original problem. And we saw in Dr. Rosen's talk beforehand that for certain problems, we have these guarantees that if our data is nice enough, not corrupted by too much noise, we can expect that for surprisingly complex problems, right? SLAM on the scale of, thousands of poses. It's really interesting that we can quantify a theorem that beforehand tells us if our data behaves nicely, we get this simplified scenario, mind you. Okay, so looking again at this parking garage example, I want to talk about the benefits of this approach to the practitioner one more time. So first one is that there's no initial guess required. So depending on your domain and what problem you're solving, you might need to have a custom initializer that an operator or engineer with domain expertise needs to provide. So with convex optimization, we can dispense with all that. So from a practitioner's viewpoint, I think this is the big one. Like, wow, I don't need to have a separate initialization phase for an optimization problem. Then we have this certification property that Dr. Rosen talked about. So we can, once we've presented the method with a solution, we can certify the one on the left as being the global minimum. The one on the right does not sort of pass that test. And then the third one, which was also hinted at, is that at least in part of our perception pipeline, having something that gives us a layer of certainty or at least some sort of mechanism to reflect on the data we've already collected and say, hey, this part doesn't work. It's good for building sort of a perception backend, and how to combine this with deep learned models for the front end for extracting features is very exciting. And to be able to sort of push maybe the uncertainty from learning-based models, which are kind of black boxes a lot of the time, into part of our pipeline for processing spatiotemporal data, I think is a very appealing choice for designers. So keep that in mind. The other thing I want to stress, just going back to this quickly, is that today, so Dr. Rosen's talk was about something that's mission critical, right? If you're mapping and you have a big error, you might crash a car, have something catastrophic. Today we're going to talk about first designing where to place sensors. So even though we might not get exactly the global minimum, our convex relaxation still lets us quantify how far we might be from the best possible solution. So keep that in mind, just as a difference about these talks. Okay, so let's move on to the first of the two problems. So where should we put the sensors? How should we design a perception system? And the first example of this is when we have a robot that's tasked with simultaneous localization and mapping, or SLAM, of an unknown environment. And we can see the robot has some trajectory. So that's our next assumption here. We know that this robot, maybe it's a service robot in some commercial setting, has a rough trajectory that it's going to follow. So it could be serving customers in some commercial setting, or in an industrial setting, it's a mining vehicle that has a predetermined route. Okay, and we also might have a rough map or idea of what our environment looks like, so a distribution on the landmarks. We don't know exactly where they are or what they'll be, so we're going to do SLAM, it's not localization. But we have a sense of where things are going to be. And the obvious one for vehicles is like, if it's outdoors, there's not going to be as many reliable features in the sky, for example. We're going to concentrate features on the ground, and we might know which areas are built up, and we'll have a lot of nice rectilinear features, for example. So the question becomes, where should we mount our sensors? Perhaps we have a budget that lets us mount 2 sensors on a vehicle, and we've got C1, C2, and C3 in this toy example. So there's these 3 candidate sensor positions, and the lines I've drawn between the sensors and the landmarks are measurements that we predict. So this is all before we actually go and deploy the system. This is all in simulation, and you can use higher or low fidelity simulations here. Which of these 3 cameras are most valuable to reduce the error in our eventual estimate in SLAM? That's the big question we're asking here. Okay, one more problem just to really hit home what I mean by design of environments. If instead we're able to not place sensors on a robot, but put beacons or fiducial markers that the robot with its existing sensor can localize against in an environment. So that's these 5 gold squares here, A1 to A5. We have this set function maximization problem. We have a cost function there, or a score function we want to maximize. We can only choose K of these 5 beacons. So instead of it being cameras mounted on a robot, we can have infrastructure in the environment, and we can't, it costs money. We can't place all of it, or there might be other restrictions in place. And it comes out basically to a similar formulation here. But these 2 problems are the type I'm talking about today. Okay, so what are we going to use as our objective function here? What will quantify a good solution? So the Bayesian experimental design literature has inspired a lot of techniques in robotics for deciding which measurements to keep when you're doing something like SLAM. And I'm going to commit Gaussian primes here. Dr. Xu will be very disappointed. We're going to assume everything is Gaussian measurements and that our posterior estimates are all Gaussian. So great direction for future work is how do we make this more complex. So it was, bear with me for now. I apologize for the Gaussian focus. But basically what we want to do is say, okay, every time we add a beacon and get measurements from that beacon to a particular pose, our predicted covariance, sigma check here, is going to change. And we want to, for some notion of the size of the covariance ellipse, the expected covariance, we want to make it small, basically. We want very small uncertainty in our estimate. So the way we're going to do that is we have this set function maximization approach where we're choosing a subset of our sensors, and at most K of them. K is our budget, the number of sensors or beacons we can place. And we're going to use the log determinant of the Fisher information matrix. So don't have time to get into all the details here, but we're maximizing here. You can think of, through the Kramer-Rao lower bound, the Fisher information as sort of the inverse of the uncertainty. So instead of minimizing the uncertainty, we're maximizing the Fisher information. Same thing. So that's what we're maximizing here. And this is called de-optimality in that Bayesian experimental design literature. And this is essentially maximizing or minimizing the volume of that ellipse. So the cool thing is that for this particular choice of function, we have a property called submodularity, which I'm going to gloss over, but it basically says that it's diminishing returns. So the more measurements you get, the less gain you get per measurement to your cost function. And that's an intuitive notion of it. It's a little more precise. And the cool thing about submodularity is it leads to a suboptimality bound for greedy solutions. So if SG is a greedy solution with K steps, we're just one at a time picking the next best sensor and doing that K times, we get within a factor of about 0.63 of the true optimum S star. And something to say about this sort of combinatoric function, they are in general NP hard. So this sort of approximation is very good news for us. It's not exact, but we can get within some quantifiable known bound of the best solution. Okay, similarly, we can do what's called e-optimality, which is instead of minimizing the volume, says, let's minimize the largest axis of that ellipse. So it's trying to encourage isotropicity while shrinking it down. So a different approach than volume, but same idea. And the advantage here is that this gets much easier to compute as you scale up your problem size. That for reasons we can talk about, it's time for questions, but I can't get into them with the time constraints right now. And what we can also do now is finally getting to convex relaxations. So instead of saying, okay, we're choosing K of these cameras, and they're on or off, we only pick one or another, we do a convex relaxation called a Boolean convex relaxation, which instead says we're going to allow a fractional amount of each sensor from 0 to 1, and all those fractions have to sum to K. But we're doing this non-physical thing where you can have half of sensor 1, half of sensor 2, that only counts as 1 in your budget. So we're going to see where this takes us. And the reason we do it is that e-optimality leads to a convex optimization problem, which we know we can solve to global optimality. So we're going to do that extract solutions, see if they're close by checking that suboptimality bound. Okay, so I hope that's clear so far. Visual summary. Each of these cameras, C1, C2, C3, is one of our decision variables. The sum of these variables, C1, C2, and C3, has to equal 2. We can only pick 2 cameras, but each of them can be between 0 and 1 instead of on or off. And this obviously is more valuable as we scale the number of candidate cameras, because for low dimensions like this, you could solve the combinatoric solution by checking 2 to the 3 possible solutions. And we've got our maximum e-optimality function there, and you can see the effect of each variable on it. So this is what we're looking at. We call this OASIS for optimal arrangement for sensing in SLAM. And just looking at the experimental setup, we did 3D trajectories, some structured like a circular trajectory or line, and then we had these random walks, and we had a synthetic distribution of landmarks. That's those blue stars on the right. And these preliminary results, which were at ICRA this year, show some cool stuff. So each of these little pizza slices here is one candidate position for our camera. And we're picking, say, K of these. And one cool thing that the solutions we got, so the darker the pizza slice is, the better our optimizer told us it was to choose. So we want to pick the K, round down to the K best of these candidates. And one thing that's cool is in the linear case, we actually see a heuristic that a human designer might have chosen recovered, which is wide baselines between cameras, right? The wider your baseline is, the better you can resolve distant features. So it was interesting to see that emerge in the data. And the important thing to note is this is environment specific. So for different trajectories with different distributions of landmarks, we might not see this effect. And this is meant to be a bespoke tool that you design for your own sensing scenario. On the right, we had a square set of positions to place things on. And then once again, we discretized the angle at which we could place each camera. And you can see there's a preference for these corner spots. And once again, very problem specific. Back to the convex guarantee stuff. On the left, we have our objective score. And the brown line at the top is the convex relaxation that is our upper bound on how good the solution could be. And we have the certification property here in that our relaxed solution, when we round it, we get the gold curve, and the greedy solution is in blue. And you can see that at around 3 sensors, we're quite close to the optimum. We can look at that little gap and say, this is at worst how much off from the optimum our objective is. So very cool to see that in effect. We know for K equals 3 that we're actually really close to the true optimum for this problem. And then on the right, I just wanted to show that this information theoretic objective function actually tracks with the real world metric we're interested in, which is the root mean square error of the translation. So as you can see, the greedy and relaxed solutions for 2, 3, and 4 cameras are much better than the others. When you start selecting more cameras, it kind of all comes out in the wash because there's just enough measurements. But nice to see that our objective function matches what we want in reality. In terms of preliminary results for this beacon placement problem, if you have an office traversing a robot traversing some office or industrial setting, and you have these red crosses represent candidate positions to put a range beacon. You can do something similar, and some preliminary results, we haven't done the convex relaxation approach for this problem yet, show that you get this bound as a blue line from the brute force optimal solution for small problems, and our greedy algorithm is actually getting very close to the true brute force optimum here. So that's very preliminary results, more to come on that in future papers. Okay, so we've taken a look at a framework for placing sensors or markers in an environment that leads to good performance down the line when you're actually doing SLAM or localization. So the question now is, once we've decided where to place the sensors, we still need to get a very accurate estimate of where all of them are. So here's our 8-camera experimental rig, and we want to know relative to one another the extrinsic calibration, the pose and 3D space of each of these cameras. And in 2022, Wang and others adapted the classic Hyundai and robot world calibration, also called AX equals YB, to support multiple sensors and targets. And the idea here is that you've got a loop with some unknowns, X and Y, and measurements in the form AI and BIJ here. So here we've got cameras on a car, numerous cameras indexed by XJ, and then you've got a tracking system like Vicon or whatever that gives you very accurate tracking of these markers on the checkerboard. And you've also got the checkerboard being observed, that's these AIJ measurements by each camera, and you can form a nice optimization problem from that. So Horn and others last year took this idea to the intelligent transport sort of sector and had a paper on doing this for infrastructure cameras mounted on various parts of civil infrastructure, and then they put the target on the car. So there's different variants you can look at, and we're going to talk about the results of this compared to our approach. Very quick recap, because Dr. Rosen already did a good job introducing everyone to this, but that AX equals YB formulation is once again just something that looks like this QCQP, and you can do basically the exact same convex relaxation that he used to get a semi-definite program. So we won't go over that again. And in this case, we have sort of a partition of the two types of variables. There's cameras and markers, so there's M cameras and P markers. And yeah, we can solve that for the global minimum using convex relaxations. So Wang and Horn, prior work in this problem formulation, only considered the following sparse simplified configurations, where you either have one target and many cameras or one camera and many targets, which for civil infrastructure is like a limitation. You want to be able to have both. You might want a fleet of cars with targets on them and then many tens of sensors mounted to the infrastructure. So that was a limitation we removed. On simulated data, we do a great job outperforming the other two algorithms. So Horn's method has some issues because it uses dual quaternions. You have to sort of parameterize it. There's like an extra step to get it to work, and it didn't work so well on the simulated data. So we had about an order of magnitude less error, and we outperformed Wang's method as well in terms of both translation and rotation error in simulation. For a real-world experiment, we took that 8-camera rig, and then we placed 16 April tag markers in an indoor lab/office environment. And here's some example images captured by one of our cameras. I mentioned that we can do arbitrary graph structures. We don't just have to have one camera or one April tag. So this is a grid view, sort of an incidence matrix between camera and marker observation. So much more complex. The color here means something a little different. So red squares are when measurement did not have enough information to do a pairwise calibration of just those sensors. So that's for future work down the road. But the idea here is just that we have this arbitrary bipartite graph visualized as like an incidence matrix here. And our final experimental results for this real data set, we have a few variants of ours, some that treat the April tags as having unknown size, and these cameras are monocular, so you have to estimate the scale as well. But the performance was very good across the board, and there's a lot more to come in the full paper very soon. So in conclusion, presented two sides of this important problem of getting cameras out there in the wild that I hope intelligent transport systems researchers are interested in. I have to think, the future work is to get more experiments out there, both simulated and real, and sort of build a software package that can allow non-expert users to just play around with this. Design heterogeneous systems. So I was looking at either just range sensors or just cameras. So mixing them and seeing, okay, in some scenarios, is one of the sensors better than the other? And do we get an interesting mix? Something we've already talked about today, but robustness is a big idea here. Outlier rejection is really important. And then scaling this stuff up to urban infrastructure, which might involve thousands of sensors and thousands of targets or more. So that's a challenge as well. And my external collaborators are Pashami Kavedi from Northeastern, Professor Dave Rosen, you've already heard from today, and Emmett Wise, who's at Wabi working on some very cool problems for autonomous vehicles. So they were pivotal in this work. And then thank you, everyone. Please check out my lab website. We're a new lab. We're growing, always looking for collaborations or people willing to work on these problems. So check out arcolab.ca, which will be updated a lot in the coming year. And yeah, happy to take any questions.
Thank you so much for your such interesting and informative topic. Any question?
Where the paper will be published?
For the calibration stuff, probably IEEE. I can just send it to you. Transactions on robotics. Well, I'll send it to you. Yeah, transactions on robotics is where I usually. Yeah.
Anyone else?
Yeah, thank you for the nice talk. I'm always amazed when somebody said lower bounds and upper bounds. but my question was, you said you want to combine different sensors. And what I was asking myself, do you plan to include also a measurement for crosstalk? Because I believe if you go further from cameras to other sensors, this become a problem in the perfect placement.
Oh, I haven't thought of that. That's an excellent question. Yeah, so right now we are assuming this kind of independence of each selection. It's kind of crucial for the mathematical techniques we're using. So no, I haven't considered that, but it is definitely a concern. And I think it would, I'm not sure if it would completely ruin this approach of set function maximization. It might just really complicate the function structure that we get that would, yeah, destroy maybe some of the nice properties, but I think it's a worthwhile challenge because you're right. Other sensors don't play as nice as like sort of passive monocular cameras taking in light. Great point. Yeah.
Sorry, what was the question?
About crosstalk between sensors that are a bit more complicated potentially than.
Maybe also the channel model plays a role, and you need to stick this somehow in the model.
Definitely.
Which I think is a really nice challenge.
Yeah. No, that's a good one. I had not thought of that. Very cool.
Any question?
So if you go back to one slide you show, okay, for the visual information. So also in here, so the measurement for. So for the measurement, for example, this landmark. So this measurement is like this is a visual reprojection, or it's like directly it's a range measurement.
This is so we're treating these in this example as they're actually each stereo cameras. So it's just like a point to plane projection for a stereo camera model. Yeah.
So and also I mean for when you do the experiments, I can see you get like 8 or 12 cameras, right? So actually I mean if you want to calibrate, for example, this of course you solve this problem. So usually when we collect the data, it's hard to convert that all image from different cameras are collected at the same timestamps.
Yes.
So it means actually if you calibrate like Gen 6, it means we are talking about spatial. So actually, I mean, the time differences can also be Gen 6 parameters. You also consider this.
Oh yeah, for the calibration side of things. Yes, definitely. So being able to incorporate temporal offsets into the global optimization view and the polynomial stuff is very challenging. I've tried. Haven't given up necessarily, but I think it might be, for now at least, it's something that needs to be done in 2 stages. I don't have a way to lump it in yet and use these convex optimization techniques. Don't have that.
That means, when you do an experiment, you directly do, for example, like 2 times or 2 ways, like you can directly trigger the data collection with the hardware. So do you do this, or you directly check image from the set timestamps?
Yeah. So. So there's that little board on the top right you can see that's synchronizing measurements here for this experiment, but that's especially in we're trying to calibrate citywide or something, and we've got maybe different sensors that are not on the same board like this. It's absolutely a challenge. But here we circumvented it for this experiment. But this is the kind of thing that I'm interested in hearing about from this community, where you don't have just a robot with everything connected. So very good point. Yeah.
Okay, so let's talk, because currently we are also doing the similar stuff. So currently previously we have a sensor kit with different sensors.
Okay.
So recently we try to refine the sensor kit because we wish to collect 360-degree image. This means we need to at least 6 cameras.
Wow.
So we also have similar problems like the spatial and the temporal. Yeah.
Okay. Awesome. Amazing.
Yeah, no problem. Paper.
Cool. Yeah, I would love to talk about that further. Amazing.
I have a question. So, actually, I used to work with large vehicles. You imagine that we have ships, which has 90 meters of length and 10 meters of width. And if you want to deal with the sensor mounts, or you want to mount sensors, it will be quite challenging. And how do we scale your method of those kind of optimization-based methods from a mathematical point of view to large vehicles? This is the first question. Second question here is, I know there's another research perspective called robot information gathering. Do you know the work from Professor Popovich from TU Delft? She was with the University of Bonn.
Okay.
So try to take another. Try to go from the control perspective. Try to get the perception uncertainty, for example, or transaction information called into the control pipeline, try to get more information. So how do you, could you share some insight on that?
Yeah.
A similar concept for information errors.
Yeah, no. So for calibration, I'll answer the second question first. In terms of the controls perspective, so designing maneuvers for, say, a calibration vehicle to drive around this infrastructure you've set up and have enough motion that everything's observable, that's a problem I'm actively looking into. So for the calibration side of things, for this design and the sensor placement, I think there's a lot of overlap. So the submodular greedy optimization stuff, like the controls community has done a lot of sensor actuator placement problems. Like that's been studied before. So I'm taking inspiration from a lot of that. Not familiar with the researchers' work you mentioned in detail. I should check that out for sure. But yeah, no, there's definitely, especially for the calibration side, taking a controls perspective and trying to figure out how to efficiently design movements that give you high accuracy in terms of calibration is key. The first question about scaling up. So do you mean in terms of just there's so many places to put the sensor on such a large vehicle? Yeah.
That want to dismount a sensor and replace it to another place. It's very difficult to scale to very large vehicles.
Yeah.
Maybe you have some insights how to take from the view of your method to scale for this kind of problem.
So I will say that this approach using the e-optimality, so this minimum eigenvalue lambda 1, does scale quite nicely, so long as you've got at least some kind of sparsity in your information matrix. But there's still, it depends on exactly how large you want to get it. For the greedy stuff can get pretty slow as you, well, it's still decent. Really good question. Yeah, it's an active thing, but this approach can scale up quite a bit. We haven't pushed it yet. That's something we're working on. Yeah, good question.
Not putting a question, but you were mentioning fiducial markers, and I was thinking, you have in every country we have this geodetic offices which are in charge of maintaining them and tracking them. Do you think that in the future there should be maybe some other complex systems or something else that would be useful not only for putting this laser total stations and stuff?
Oh, so sorry. What kind of offices did you say at the start?
I was thinking about these geodetic offices where they say they have this collection of fiducial markers that they have precisely.
Oh, like surveying and stuff.
Yeah, surveying stuff.
Oh, yeah, that's really interesting. Yeah, I definitely think you can kind of kill two birds with one stone, depending on if civil infrastructure for stuff like that needs this as well. I think that would be a great point of cooperation, actually, because it doesn't have to be a particular type of marker, and we're working on the front end detection side of things related to the robustness as well. Maybe not having the exact set of markers you're going to find, so existing civil infrastructure could be used in this way quite nicely. Does that kind of answer your question?
Just a general question.
Gotcha. Yeah. No, I think it's definitely feasible. Is there time for one more in the back? Sorry.
So I have what? So we also have infrastructure sentinel project. But one big issue we have is that when you somehow try to optimize the location of the sentinel, what if there are some trees, some obstacles will block your acquisitions or lineups? Is there any way to do that?
So you're talking about the sensor placement, the design part? Excellent question. So, my colleague was asking about occlusions from, say, a tree in the environment, blocking maybe a LiDAR sensor or a camera. And when setting up the problem in this way, so I made a sort of implicit assumption I didn't go into, right? So we're claiming that we have all these candidate poses, C1, C2, and C3 on this slide already. So it's a discrete set, and we're doing the set function maximization. So we are assuming, baked into our design problem, that we know enough about the area we're trying to design our robot or our, so if it's the SLAM case, we're assuming that there isn't going to be some unknown obstacle. If we know about the environment to some extent for, say, localization, not for SLAM. We can model occlusions, and then these edges here all represent measurements. We can just sort of prune those that might be occluded based on existing stuff in the way. That works for localization. For SLAM, it's a little stranger. Like, we're assuming that we have some limited information about the environment, and this could be a problem, what you're describing there, for sure. But I haven't explicitly accounted for it in this setup yet. But the cool thing, though, is that this assumption that we have a discrete set of poses sort of lets us do this design in a way that's easier than if we just had, say, k variables representing sensor poses and did a continuous optimization approach as opposed to set function maximization. There's been work on that, but one problem there is that you get something very non-smooth because of occlusions. Because we're not restricting our sensors to a fixed set, we have to consider very non-smooth objective functions resulting from that. And it would be more of a problem in that setting. Not impossible, you can do non-smooth optimization techniques, but it's highly non-convex, not clear how to do a globally optimal solution to that. So yeah, it's just some strengths, I think, of this discrete formulation. Great question.
Thank you. Thank you for the introduction, and thanks for inviting me. So today I'm going to talk about the Gaussian splatting based NAND. So first I would like to introduce the story behind that. So why we're going to do some research about this Gaussian splatting based NAND. So when I first read the paper about 3D Gaussian splatting, I find out, okay, this is very interesting topic. Then I talked to two of my graduate students, Zerling and Ria here. So I say, okay, why not try to do something regarding the 3D Gaussian splatting in your own research? So then Zerling did something about using the Gaussian splatting in the navigation side. So that's his work. And we can see he's kind of hiding here. Probably because he didn't give me too much result for this work. So this time he chose to hide. And what's Ria? Here is a lady, Ria, smiling here. So that means she gives me some results. So let's see the story. And for this outline, we will start with 3D Gaussian. So I will briefly review what's a 3D Gaussian and what we have done using the 3D Gaussian in the SNAM parts regarding the mapping, also the navigation. No? Since this one doesn't work.
You can use this one.
Yeah. Okay.
And if you start on it, it's supposed to.
Okay, cool. Thanks. Okay, so let's start with a 3D scene representation. So as we know, the 3D scene representation can capture lots of information of the real world, such as geometry, lighting, appearance, sometimes even physical, right? Physical means if there's two objects, even if they have contact with each other, some of those like 3D scene representations can show that. Okay, so most common ones we can see we have the point cloud, voxels, and mesh, right? So those are all explicit, and all of them have some limitations here listed here, right? Then we also have the implicit, right? So the most popular one is the LUF, right? So we can see the LUF is basically to use the Liouville field to learn the information from the input here, 5 positions, 3 parameters, and direction 2, and also to output the color and density, right? So it's implicit representation of the 3D scene, and is very, high photorealistic, but there's some efficiency limitations. So every time when there's a new 3D scene representation, it will trigger lots of research in relevant fields such as SNAM or the relevant ones. So we see a lot of publications about LUF, and then people will think, is there any other better 3D scene representation that can combine? Okay, whether it can combine the high quality, also the high efficiency, right? Then that comes to the 3D Gaussian. So what's 3D Gaussian, right? If we write that in this equation, right? This is what we get here is a 3D Gaussian. I'm surprised today we have lots of discussion about Gaussian. That's about 200 and 300 years ago, right? So here also we use the 3D Gaussian to to do some work in the stem side. Sorry. So how to describe a 3D Gaussian, right? So the basic information, if we want to describe a 3D Gaussian, we need those like four types of. Sorry, probably I need to get some water. This happens sometimes during my teaching as well. So my students are used to this. So basically, we will have 4 categories of parameters. The first one is a mean. Mean value, we will have the 3D position, x, y, z, and then the variance. Variance is used to describe the volume of this like 3D Gaussian. So basically, we use the scale and the rotation. That breaks this into 7 parameters. Scale with 3 parameters and rotation. We use cotannion here to describe the rotation. So we can see, and also we have the color here, right? So we use spherical harmonic coefficients to describe the color. So why we want to do that? Because we want to make sure if we look at different view, the color will be different to make it more photorealistic. And then we have the opacity. So that will be used in the alpha blending, because sometimes for each pixel we have multiple Gaussian splattings will affect that. How to combine them together, we will depend on this opacity. So on the right side, we can see there's a 2D peak here. So this basically trying to show, okay, if we change the scale, right? Because we have 3 like parameters. Actually, here is a 2D like that 2D demo here is if we change the scale, how the Gaussian will change also the rotation, right? If we change the rotation, so how this Gaussian will change in the space. And let's move to the 3D Gaussian splatting, right? So from the name, it seems like if we have a 3D objects, we just splat that into a 2D plane, right? So this is what happens when we call the 3D splatting. So basically, we will start with some existing 3D Gaussians like this, right? Once we have this as a first step here, so we have already well-constructed 3D Gaussians, and then we need to do something to split that into 2D. So first step is we need to do the cross-term counting here. That means we need to, based on the view and the camera information, to detect, okay, whether this Gaussian can be observed or not. If it's not observable in this view, we will remove this Gaussian from the list, right? So this is the first step. And then the second step is to do the projection. Right? So from the 3D to 2D. So as we know, to describe the 3D Gaussian, we have those 4 categories of parameters. We have the mean value, x, y, z. We have the variance, we have the color, and we have the opacity. So the 2 main things we need to project is mean value and the variance. So this is a formula here. So first one we based on the camera like calibration parameters, extrinsic and intrinsic. And the second one is actually very interesting for those who are interested in the math. So you can do some derivation about J especially. So W is a viewing transformation and J is projective transformation. So there is some approximation here to make it linear. So very interesting. So after we have this transformation, 3D to 2D, we might have multiple Gaussians there, right? So then we will need to think, okay, how to combine those information, the contribution on specific pixel, okay? And one thing I want to mention here is compared to the LUV, right? Because LUV is very popular because it can provide very high quality, rendering effects. So one limitation is rendering efficiency. So because LUV requires to sample the information along the ray. So that means because it's implicit expression, right? So it means you need to do some sampling on the ray along the ray to get the information. But for Gaussian, we just need to figure out, okay, if this is correspond to this ray, we just need to do the splatting so it can improve the efficiency. So this is one difference between the LUV and the Gaussian here. Okay, so this is a flow chart or overall pipeline of how we are going to optimize the 3D Gaussian, right? So we will spend several slides to break down this, this flow chart. So the starting point is the very sparse points, right? So we can use SFM, so that stands for the structure from motion, right? So we can use, for example, COMAP or those like popular ones, open source ones to generate the initial points here. It's very sparse. So we start with sparse points here, and then the second step is to initialize, right? So initialize means from the starting point, we need to initialize the 3D Gaussians, right? Because 3D Gaussians, we need those 4 categories of parameters. And after that, we will do the calibration, right? We will do the projection. That's basically the splatting. So we will splat the 3D Gaussians into the 2D using the calibration parameters. So we have a camera here, right? So this means calibration parameters. And then we will do some tile rasterization. That means we need to combine the contributions of each Gaussian into the specific pixel and to generate the image. And then we can compare to the original image, right? 2D, then backward is we can calculate the loss function and calculate the gradients, and we use gradient descent here. So there's no much complexity in the optimization part. It's very straightforward. And we also have adaptive density control here. So we'll see what it means, the adaptive control here. So from this high level picture, we can see we start from very sparse points at the very beginning, and then we move to this. This is actually a 2D Gaussians, right? This is the image of 2D Gaussians. If you look closely, there's some like ellipse inside, right? So after all this step, we will have the image. It looks very real, right? It's very photorealistic. So we'll see the detailed steps. Okay. So this is a forward part. So that means if we have sparse, like a point cloud, how can we get to the image step, right? So we start with the sparse points. So we have the color and the mean value. So that means we load the position and the color here, and then we do the initialization, right? So here you might ask one question. I only have the 2 parameters here, and how can I get the other 2, right? For example, the coherence. How large is this like 3D Gaussian, right? So in the original paper, they use a KN algorithm. So they basically to find the nearest 3 points and then use average distance to use as an initial value for the variance. So in that case, the 3D Gaussians they generated can basically cover the whole image. So this is coherence, and opacity usually is initialized as a very small value or even 0. So then it can be optimized. And then the projection, as we mentioned, this is basically the 3D splatting step. So we project from 3D to 2D. Then after this step, we have a bunch of 2D Gaussians, and then we will do the rasterization. So we will see what happened there. And after this step, we have the predicted image. Kind of we can use original image as a label here to calculate the loss function. So this is a forward workflow. And this is how also one key point why the Gaussian splatting is very fast, right? So it uses tile-based parallel rendering. So that means it will split the whole screen into like small parts. So we call it tiles. So usually split into the 16 by 16 tiles. So for each tile, it will do something to speed up the processing. So inside each tile, so what will happen is first, we can see on the above part, we will do the splatting, right? So let's split 3D to 2D here. And then what happened here? Because for some of the Gaussians, it might affect more than one tile, right? So in this case, we need to do a replication. That means if, for example, this tile here, it affects both tile 1 and tile 2, I will do the copy here. So for this Gaussian, I will have effect on tile 1 and tile 2, right? So then one thing here is to do the sorting. Sorting here is very interesting. Actually, it's based on a key map data type. So the key is composed of 2 parts. The first part is tile number, and second part is the depth. So that means after this sorting, so we have associated tile information and also the depth from in a ascending order. Then based on this, we can do the parallel rendering here. So this case shows if we only have two Gaussians affect that pixel, what we should do, right? It's basically the standard alpha blending algorithm. And also very interesting part here is how to speed up, right? This is also one key here. My student Zhening was lost here when he checked the CUDA algorithm, how the CUDA is used here to speed up the processing. So basically, when we process each of the tile, so all the pixels do the same iteration on the list, on the sorted list. So that means all the pixels only need to iterate the Gaussian list once, because this already arranged in the depth order. So we just need to from the closed list depths and to the farthest, and then we can do the alpha blending. In this way, each pixel can use one GPU thread and to do the parallel processing, because all the information here is kind of sorted. So this is very GPU friendly, but not user friendly. Okay. So this is for the tile parallel rendering. And for each pixel, as we mentioned, if we have multiple Gaussian affecting one pixel, right, how to combine them together. So this is actually the standard alpha blending here. So basically, we need to calculate the contribution of each Gaussian into the pixel. So basically, we need to apply this function here. So this function here is to calculate, okay, if we have a 2D Gaussian here, if we load the mean value and also the variance, how much did it contribute to this pixel? And then we can base on this equation here to combine all the Gaussians that will contribute to this pixel and have the final color here. And backward, right? So we have talked about forward. Forward, that means we can start from these SFM points and to generate image. Then we need to think, okay, now we have some prediction of the image. How could we update the 3D Gaussians, right? So basically, we need to calculate the loss function. So loss function here is expressed as this. So it's combined of two parts. One is L1, L1 plus is combined of this photorealistic, and also there's some regularization here to keep the isotropic, property of the Gaussians. And also there is structure similarity, index measure. So this usually is set as 0.2 in the original paper. So after we have loss function, we can also calculate the gradients, right? So gradients, there's very detailed, derivation in the original paper. And the interesting actually is happening here, right? So usually we just did one error, right? To either change the original 3D Gaussians based on gradients. But here there is adaptive density control, right? So basically it will be used to change the number of the 3D Gaussians, right? To 2D Gaussians here, okay. So we'll see that very soon. Okay, so that means for the backwards, we will use the gradients calculated and also the loss function to change the 3D Gaussians. 3D Gaussians here means we have the 4 categories of parameters, and then we use adaptive density control here to do some change on the Gaussian that we'll see very soon. Okay, so adaptive density control here, right? So as we promised, so we will discuss, because if we take a look at this part, so the original number of these 3D Gaussians are defined actually from the original point cloud. That means if we input 1000 as FM, if you don't do any change about this adaptive density control, finally you will get 1000 point cloud, right? So, but here, if we have something here, we might be able to, based on the real station, to adjust the number of the 3D Gaussians, right? So this is actually a very important part. So let's see what happened. Right, so basically there are 2 types of change. So one is to add more Gaussians and the other one is to remove some Gaussians. So to add some more Gaussians, so in some cases, we are mainly based on the gradients. So if we, based on the gradients, if it's too large, so the gradients with respect to the geometry, if it's too large, that means we need to densify this area. So also inside there's 2 types of the density phi. So one is called under construction, the other one is over construction. So if it's under construction, so what we need to do, right? So if it's under construction, we need to clone here, right? So you can see we clone this original to to two Gaussians, and we also do some change for the original Gaussian. And for this, over construction, we split, right? So we split a larger Gaussian into a smaller ones. We change the scale as well. So these are two situations are based on the variance. So the number of variance we set as threshold, and then we can do the change. And then the points ruling here is more straightforward. If Gaussian after training, if it's very transparent, so that means opacity is close to 0, or that means is less contribution to the overall pixels, then we will remove it. And then we will talk some of our work, right? So basically the idea is to incorporate the 3D Gaussians into our work. So because Ria is doing something about SD map updating or SD mapping using the cell phone, right? So initial idea is I talked to her, which sensors you're going to choose, right? Because she knows my number one sensor is GNSS, but she prefers to use IMU and camera, right? So this work is done by integrating the IMU and the camera. So actually there's this flowchart. It's not very clear. Actually, at the very beginning, we use a COMAP to generate the SF points. COMAP is used first, and then we use RBSNAM3 because it has the MU inside. We recover the scale. We use that to calculate the transformation between the COMAP point cloud and the RBSNAM3 point cloud, and then we use that in the 3D Gaussian. So the overall flow is shown here. So for IMU part, we did a little work because IMU inside the cell phone is not that very accurate. There's some noise, so we did some smoothing. So I believe here we use 5 seconds sliding window to do the smoothing, and then we use RBSNAM3 to fuse the MU and camera together, and then in the 3D Gaussian part. So the usage of the 3D Gaussian in this work is to densify the point cloud. As we can recall, we have the adaptive density control part, right? So we can generate more points, right? Also, that can still be photorealistic. So we can see here, this is the original IMU smoothing part, and then we have the RBSNAM3 output, and then finally we have the 3D Gaussian, the densified result. Okay, so we'll see more results later. So this is experiment part. So we did the data collection in Calgary. So that's about 3 hours driving from here. So we have a very short, we did several loops here, and this is Google Web for this position and some of the, the images we have from this data collection. So that means for this work, we're trying to use the cell phone here to capture the map updates, and the base map is based on this data reference system of data collection platform on the right side. So we have very old 116 LiDAR here. We have also Paul and you here. Actually, we are working to upgrade this data collection platform. Hopefully, we can get the funding. So this is basically we want to use this cell phone, data to do some map updating. So let's see what we have. So first, we also did some stochastic model, right? So that's usually we use univariance. But one thing we need to keep in mind, sometimes univariance gives us too optimistic results, right? So that's usually in engineering, we need to do some fine tuning. So for example, we apply a factor of 3 here. So we find, okay, if we apply by 3, seems looks good for this result. And then we do the smoothing we mentioned earlier. So this is for the smartphone MU part. And the RBSNAM3 part, this is very standard. So we didn't change any keyframe, selection criteria. So those are the criteria we use. And on the right side, we can see, okay, if we use RBSNAM3 based on the cell phone data, we can detect the loop closure, right? So that's something we will see for the COMAP. Sometimes it cannot detect the loop closure because it's used on sequence images. So next step is, as we mentioned, we will first to use a COMAP to provide colored point cloud, and then we based on the scale information from the ORB3 point cloud to kind of recover the scale, right? So we use this square here to recover the scale, rotation, and transmission parameter scale. And then of this, we will input the recovered point cloud to the 3D Gaussian, and we can have the densified results. You can see all the points increase a lot. It becomes over 3 million, right? So that's a lot of points. And here it actually, the student want to show, okay, if we use a COMAP with different sample rate, it cannot detect loop closure. So the reason I still ask her to verify, is this your work or is the COMAP's issue? And for all these snaps, we can see we can detect loop closure very straightforward. And this is some samples if we have the image and what the final the 3D Gaussian point cloud looks like. And we have one more result about the mapping part. So if we are going to say, okay, if this is point cloud we generated from the cell phone, and this one, so we use the FastNeo here, FastNeo 2 here to generate the base map. If we do the registration, what it looks like, so if we go here, we means we do the registration of the new point cloud into the base map, and then we also have an initial evaluation about the, accuracy of the, the point cloud generated from the cell phone. So the value is scale factor. We have 0.913. So scale error is about 8.7% compared to the original ORB SNAP3 in the indoor metrics. That's about 2.2. I think we still have some room to improve. And the RMS here is 0.3493. So this ongoing research, now we are still trying to figure out, okay, do we have some issue on the configuration, calibration part? For example, the camera to IMU extrinsic calibration. Do we have something especially for the inputs, the initial point cloud, can we do something there? So this is still ongoing process for the mapping part. So we are aiming to have very accurate HD map updating pipeline from the cell phone directly. So later we might also need to add my favorite sensor, the GNSS, into the work. And then we also have one more, this one is kind of the registered result as well. So actually, because we are testing a very kind of controlled environments for current stage, so we are using the vehicles. So actually, what we're trying to show is the top right part is vehicle detected in the cell phone point cloud. The left point, the bottom left is point cloud from the base map. So we're trying to show, okay, if there's something changed, can the cell phone detect that and do the registration? But we don't have very a strict evaluation here. It's just show, okay, it's feasible to do that. And this is for the map part. As I mentioned, for the localization part is still ongoing because my student Zhening has get lost in the CUDA part when he tries to merge that into his pipeline. So basic idea is that we want to do some tightly coupling of the sensors. So the sensors currently in our mind is GNSS, right? So we finally have my favorite sensor here. And we have the IMU and the camera here. So we are trying to use the FGO to do the optimization. So the idea is we want to use the 3D Gaussian here to contribute to those two factors and overall to have a better estimation in the urban environment. And also one thing challenging for Zhening now, I think we are trying to also work on the dynamic parts, right? Because when you work in the real situation, you have lots of vehicles, moving objects, right? How to effectively deal with those tasks, situations is also challenging. So he also working on that, and he, instead of some results, give me some equations. So I don't want to spend too much time to explain. So basically he shows some derivations. Telling me, okay, I have gone through all the derivations. Now the remaining part is just coding I want. good is that hopefully before the end of this year, by the end of this year, we will see some work from Zhening about how we tightly incorporate the 3D Gaussian into this like a sensor fusion network, especially if we can get some good results from the urban environment. So yeah, I think that's all. Thank you.
Because so originally we have planned open discussion for our speakers like maybe 20 minutes, but at this moment it's clear that we are a little bit overrun. So I just quickly conclude this very successful workshop to me. Okay, I learned quite a lot and I learned quite a lot from you, and also see a lot of friends. So and after I conclude this one, we are going to take some photos, right? Okay, so again I think this is a very successful workshop. It's very insightful talks. So for example, at the beginning from Professor Tim Barfoot about like very specific scenarios with nodes about the Doppler downtree stuff, and from Professor Kong Hui. I think the work from Professor Kong Hui is so actually Professor Kong Hui is quite alone because he's the only researcher in Macau working on robotics. He's quite alone because in Macau, I mean, this university is quite rich. For example, the dean of it. Okay, he belongs to the faculty of the science and technology. So their dean always mentioned to their colleagues, no need to apply the fundings because we have enough fundings already. Yeah, they are quite rich, but in Macau is quite alone because low. So currently he's also targeting on the works on some good journals like the IGR. So he had a lot of good works. But today I think he didn't introduce some works that are quite limited to the learning base, because previously he is a chief scientist in a company, so it's related to the computer vision. So that's why he's an associate editor in the IGCV. This is one of the basic journal in the computer vision field, I think. Besides the PAMI, this is I think this is another good journal. So and also for the work from so who is the third speaker? Yeah, Professor Shi. I immersed in this talk quite a lot. Because Professor Shi is my PhD supervisor before. So I learned from Professor Shi continuously since I was a PhD student from now on. So I think this is really a nice talk, and because from my point of view, if you want to introduce the integrity concept to researchers or to anyone that is not in this field in like 20 minutes, it's almost impossible for me. It's very difficult to introduce because this concept is quite abstract. So, for example, at the beginning when Dr. Shi mentioned how to start the presentation, I mentioned to Dave, okay, this is a very good topic. I always want to introduce this concept to Dave because Dave is from the robotics. And this concept is like very conceptually from the aerospace department, aerospace society. So this from Professor Shi. And also for Dave, okay, again, it's quite inspiring for the work about the certifiability and non-convex optimization stuffs. And also for Matt, it's quite interesting. I have a lot of questions in my smartphone. I take image for your work. I will learn from your work later. So finally, it's a very good talk from Dr. Yang. This about 3D Gaussian splatting. So recently we are also we're working with Dr. Shi on one concept. For example, the idea is roughly like this. So you see the 3D Gaussian splatting can represent, for example, in your slide you mentioned differentiable. We are able to represent the scenarios with a differentiable function. So for example, radio signal, okay? So today here we have the Wi-Fi RTT. This is the range measurement from the Wi-Fi routers. So we also have the signals from the satellites, maybe from the LEO satellites, like LEO low orbit satellite from Starlink, from Elon Musk. Then we have a GPS. Different radio signals go to us. So if we are in an open sky, okay, this topic is closed. Open sky, we have very accurate positioning. Okay, no challenge. So if we get into urban scenarios or the indoor scenarios, we have reflections, right? So why we get the reflections? This is because the environments, right? So potentially we are also thinking about if the machine learning is quite powerful. It can fit everything. So can we fit
the signal transmission process. For example, if you can make the environment as a 3D Gaussian splatting, this is a differentiable function. The signal, okay, for example, satellite position and the signal transmission direction, okay, this is a non-variable. So, for example, can we design a networks with the input of the environments with the 3D Gaussian splatting? Okay, this is differentiable, okay, and also with the signal inputs, can we design a model? It's like a navigation GPT, okay? It's like a navigation GPT. So any signal get into the scenarios, we have a representation of the scenario which is differentiable with the signal inputs. We should be able to identify the signal transmission rules. If this is achievable, every correction, every errors coming from the signal reflection should be correctable. Okay, this is going to be close the topic of the signal reflection. This is my insight. Because currently I'm working on a topic with industry. It's called traffic GPT. So in mainland China, we have a lot of data about traffic. For example, like a highway. Okay, we have a lot of data. So they are working on one of the project working on the traffic GPT. It means we have a lot of data for the traffic. So similarly, so if you have large scale data for any of the reflections, for example, okay, so in Hong Kong, we collect the data set in Hong Kong all days from 9 o'clock to 9 o'clock in the evening, cross different scenarios, cross different weathers, like as mentioned by Professor Tim Barfoot. Okay, so it means all the data cross different geometry, cross different constants. So can we train a model like the navigation GPT? I think this is doable. Previously, I don't think this is doable because the scenario is not continuous. It's not differentiable. But with the help of the 3D Gaussian splatting, if this becomes differentiable, I think this is doable. So by this year, I also try to working on a project. I try to write a proposal about the navigation GPT. I try to say, if we have a scenario representation and the inputs, it should be possible. So what is the bottleneck? The bottleneck is we need to have the data set. So that's why I ask a lot of questions with Matt. Okay, we design new sensor kits with a lot of sensors. So if we have a lot of sensors and we recruit engineers, collect data across different scenarios, across different time stamps, should be doable. So that's why I think this workshop is very successful because I have a lot of new insights about this topic. And also, I think we are quite proud in terms of organizers with Homi. I think this talk is interdisciplinary enough with researchers from like Dave from Robotic Society, Matt from Robotics, and Prof from Aerospace, and Judet information from Dr. Yang and Daniel from ITS. So this is the objective of this workshop. Yeah, again, so thank you very much again for your contributions. Okay, hope we can see you again in the next year's ITS in Australia. Okay, yeah, Australia, yes, Australia, yeah. Okay, okay, thank you so much. So how many I think we can take photos in the front? That's right. Yeah, just keep